You exist inside a cosmic clock that has been ticking for 13.8 billion years, and every atom in your body is proof of it. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was forged billions of years before Earth existed, inside stars that lived and died in a universe so ancient that comprehending its age feels almost impossible. And yet we know exactly how old it is, down to the million year. We have measured the birthday of existence itself with a precision that should not be possible for a species that has only been asking the question for a few hundred years. But here is the part no one tells you. We almost got it catastrophically wrong. For decades, the numbers did not add up. We found stars older than the universe. We measured expansion rates that contradicted each other by billions of years. The math said one thing, the observations said another, and for a while, cosmology was stuck in a crisis that threatened to collapse our entire understanding of time. Then we found something. A signal, faint and ancient, hiding in the static of empty space. A whisper from 380,000 years after the Big Bang, still traveling toward us, still carrying the fingerprint of creation, the oldest light in existence, preserved like a photograph from the infancy of everything. That signal changed everything. It gave us the universe's baby picture. It let us rewind the cosmic clock all the way back to the beginning. And it revealed a timeline so vast, so meticulously structured, that it rewrites what it means to be alive right now, in this moment, 13.8 billion years after it all began. This is how we measured the age of everything. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe is 13.8 billion years old. You've probably heard that number before. It shows up in documentaries, textbooks, museum placards. It rolls off the tongue with the kind of confidence usually reserved for things like your own birthday or the year your country was founded. 13.8 billion years, clean, certain, final, except it wasn't always that number. 20 years ago, the best answer was somewhere around 13 billion, give or take a billion. 30 years ago, the range was wider. 40 years ago, cosmologists were fighting over whether the universe was 10 billion years old or 20 billion, and the gap between those estimates was so large that some of the stars we could see appeared older than the universe itself, which is a polite way of saying the math was broken and everyone knew it. For most of human history, we didn't even have a number, we had stories. The universe was eternal, or it was born yesterday, or it cycled endlessly through death and rebirth like a cosmic engine that never needed winding. Every culture had an answer, and none of them required a telescope. They required imagination, authority, and the willingness to stop asking questions once the story felt complete. Science doesn't work that way. Science is what happens when you keep asking. And the question of how old the universe is turns out to be one of the most important questions we've ever pointed at the sky. Not because the number itself is useful in your daily life. You will never need to know the age of the cosmos to pay your taxes or parallel park or decide what to eat for dinner. But because that number, that single figure, unlocks everything else. If you know how old the universe is, you know how long stars have been burning. You know how much time there's been for galaxies to assemble, for heavy elements to be forged inside dying suns, for planets to cool and oceans to form and chemistry to stumble its way towards something alive. You know whether the universe had enough time to build what you see when you look up at night, or whether something in the story is missing. The age of the universe is the foundation. Get it wrong, and every timeline that comes after it collapses. Get it right, and suddenly the entire history of everything snaps into focus. The birth of the first stars, the formation of the Milky Way, the ignition of our sun, the cooling of Earth, the emergence of life. The long stretch of evolutionary time that eventually produced a species capable of looking back and asking how long this has all been running. 13. 8 billion years is not just a number. It's the answer to a question humans have been asking since the first time someone looked up and wondered when it all started. And the fact that we now have an answer, one we can defend with measurements and math and instruments sensitive enough to detect the faint whisper of radiation left over from the universe's infancy, is one of the strangest victories in the history of science. Because measuring the age of the universe is not like measuring the age of a tree. You can't count rings, you can't dig up fossils, you can't interview anyone who was there. The universe doesn't keep records, it doesn't mark anniversaries, it just is, and it has been for a very long time, and for most of that time there was nobody around to notice. So how do you measure something that started before there was anyone to start the stopwatch? How do you calculate the age of a system so large that light itself takes billions of years to cross it? How do you look at a sky full of stars, each one burning at a different distance, each one sending light that left at a different time, and extract from all of that scattered information a single number that describes when the clock first started ticking? The answer is that you don't do it directly. You can't. What you do instead is gather clues. You measure how fast the universe is expanding and run the math backward. You study the oldest objects you can find and use them to set a minimum age. You analyze the faint glow of radiation filling the space between galaxies, the leftover heat from the Big Bang itself, and decode the patterns frozen into it like growth rings in ancient ice. You build a picture one piece at a time, cross-checking each measurement against the others, tightening the error bars, arguing over every decimal place until the number stops moving. And after decades of that work, after launching satellites and building telescopes and training an entire generation of physicists to think about time on scales no human brain was designed to process, the answer came back: 13. 8 billion years, give or take 37 million, which in cosmic terms is a rounding error so small it barely registers. That precision is new. The confidence is new. For most of the 20th century, cosmology was a mess. The measurements didn't agree. The models contradicted each other. The universe appeared younger than its oldest stars, which is the kind of problem that makes everyone involved look ridiculous. Gustav Tiemann, an astronomer at the University of Basel, once described the field's trajectory as a dramatic change from misery to glory. That's not hyperbole. That's a man who lived through decades of confusion and watched it resolve into something clean. The misery came from the fact that measuring cosmic distances is hard. Measuring cosmic time is harder. You're trying to reconstruct the history of something that happened before Earth existed, before the Sun existed, before the Milky Way had finished assembling itself out of smaller chunks of gas and stars. You're working with light that's been traveling for billions of years, stretched and dimmed by the expansion of space itself. You're trying to build a clock out of objects so far away that they look like smudges on a photographic plate. And for a long time, the numbers didn't make sense. Early estimates put the universe at around 2 billion years old. That was a problem because geologists had already figured out that Earth was at least 4 billion years old. Either the geologists were wrong, or the cosmologists were wrong, or something fundamental about the way we understood time and space was broken. Spoiler, the cosmologists were wrong. Their distance measurements were off by a factor of 10, which meant their age estimate was off by the same amount. It took decades to figure that out. By the 1990s, the range had narrowed to somewhere between 10 and 20 billion years. Still a huge spread, still too much room for error. But at least the universe was no longer younger than its contents, which was progress. The breakthrough came from two sources. First, better telescopes. Second, a willingness to admit that the universe was doing something no one had predicted. It wasn't just expanding, it was accelerating. That discovery, made in 1998 by two independent teams studying distant supernovae, didn't just refine the age estimate, it forced cosmologists to add a completely new component to their models. Something they called dark energy, a mysterious force that pushes galaxies apart and has been doing so for the last several billion years. Once you account for that acceleration, the timeline changes. The universe gets older. Not a lot older, but enough to make the numbers line up. The 2011 Nobel Prize in Physics went to the three leaders of those teams, Saul Perlmutter, Adam Rees, and Brian Schmidt. They weren't trying to measure the age of the universe. They were trying to figure out if the expansion was slowing down. The answer was no, the expansion was speeding up. And that answer, once people stopped staring at it in disbelief, gave cosmologists the final piece they needed to pin down the age with real precision. By 2012, NASA's Wilkinson Microwave Anisotropy Probe, a satellite designed to map the faint radiation left over from the Big Bang, returned an estimate of 772 billion years, plus or minus 59 million. 3 years later, the European Space Agency's Planck satellite refined that to 813 billion years, plus or minus 38 million. In 2018, Planck updated its number one more time, 798 billion years, plus or minus 37 million. That's where we are now. The universe is 8 billion years old. The uncertainty is smaller than the margin of error on most political polls. For a measurement that spans the entire history of existence, that's absurdly good. But here's the thing. That number only works if the model underneath it is correct. The standard model of cosmology, the framework that describes how the universe has evolved from a hot, dense state to the cold, expanding structure we see today, depends on a few key assumptions. It assumes that general relativity is correct. It assumes that the universe is roughly the same in all directions. It assumes that dark energy behaves the way we think it does. Change any of those assumptions and the number changes. And there are reasons to wonder. In the last few years, attention has emerged. The age calculated from the cosmic microwave background, the afterglow of the Big Bang, doesn't quite match the age calculated from direct measurements of how fast the universe is expanding right now. The difference is small, less than a billion years, but it's persistent. And the more precise the measurements get, the more stubborn the disagreement becomes. Some cosmologists think the tension will resolve itself. Better data, better instruments, a recalibration here or there, and the two methods will converge. Others think the tension is real, that something in the standard model is missing or wrong, that the universe is trying to tell us something and we're not listening carefully enough. There's even a fringe idea, published in 2023, suggesting the universe could be 7 billion years old, nearly twice the accepted value. The paper ran the numbers using a modified model of cosmology and found a timeline that fits certain observations better than the standard one. The vast majority of scientists don't take it seriously. The standard model works too well for too many things to be that far off. But the fact that someone could publish a paper proposing an age that different and have it pass peer review tells you something about the state of the field. The number is solid. The model underneath it is still being tested. None of this should be read as uncertainty about whether the universe had a beginning. It did. The evidence for the Big Bang is overwhelming. The cosmic microwave background exists. The universe is expanding. The oldest stars are roughly the same age no matter where you look. All of that points to a moment, a starting point, a time before which there was nothing we would recognize as a universe. The question is not whether that moment happened. The question is exactly when. And the reason that question matters is because time is the thread that holds the story together. If you don't know how old the universe is, you can't build a history. You can't say when the first stars formed, or when galaxies began to cluster, or how long it took for the conditions that allow life to become common. You're just guessing. You're telling stories again, the way humans did for thousands of years before anyone thought to check. The age of the universe is the starting line. Everything we know about cosmic history is measured from that point. 8 billion years ago, the universe was unimaginably hot and dense. A fraction of a second later, it started expanding. A few 100,000 years later, it cooled enough for atoms to form. A few 100 million years after that, the first stars ignited. Billions of years later, galaxies like ours assembled. 4.5 billion years ago, our sun turned on. 500 million years after that, life appeared on Earth. And here we are, the result of all that time, looking back and trying to measure the distance from the beginning to now. The fact that we can do this at all is strange. For most of the universe's history, there was no one around to ask the question. Stars burned, galaxies collided, space expanded, and none of it meant anything because there was no consciousness anywhere to notice or care. Then, very recently, on one small planet orbiting an unremarkable star in the outer arm of an average galaxy, a species evolved that could think about time on scales larger than its own lifespan, that could look at the night sky and wonder not just what's out there, but how long it's been out there. That could invent tools sensitive enough to detect the faint echo of an event that happened before Earth existed, and use that echo to calculate the age of everything. That's what this video is about. Not just the number, though the number is important, but the journey to get there. The clues that led scientists backward through time, the mistakes they made along the way, the telescopes they built, the satellites they launched, the arguments they had, the breakthroughs that changed everything. The story of how humanity went from guessing at the age of the cosmos to measuring it with a precision that would have seemed like science fiction a century ago. We'll start where the evidence starts. Not with a telescope pointed at distant galaxies, but with a faint hum of radiation filling the space between them. A signal so weak you need instruments colder than outer space itself to detect it. A whisper left over from the moment the universe first became transparent to light. The oldest thing we've ever seen, and the key to everything that comes after. We've established that the universe is 8 billion years old. That number sits at the end of a very long chain of reasoning, and every link in that chain depends on understanding what actually happened at the beginning. Not the feel-good version, not the metaphor, the physics. So let's talk about the Big Bang, and let's start by clearing up what it is not. The Big Bang was not an explosion. That word gets thrown around constantly, and it's wrong in a way that matters. Explosions happen in space. They have a center. They have an edge. Material flies outward from a point, and if you rewind the clock, you can trace every fragment back to where the bomb went off. The Big Bang was nothing like that. There was no center. There was no edge. There was no pre-existing space for anything to explode into. What happened 8 billion years ago was not an explosion in space. It was the expansion of space itself. Picture it this way. Imagine the entire universe, everything that exists, compressed into a region smaller than an atom, not packed into that space. The space itself was that small. There was no outside. There was no before in any sense we would recognize. Time, as we understand it, did not exist yet. Neither did distance or temperature in the way we measure it today. What existed was a singularity, a point of infinite density and infinite temperature, where the laws of physics as we know them break down completely. And then, for reasons no one fully understands, that singularity started expanding, not exploding outward into a void, expanding. Space itself began stretching, and everything in it, every particle, every quantum fluctuation, every bit of energy that would one day become matter, stretched along with it. The Big Bang is not a location, it's an event that happened everywhere at once because everywhere was the same place. If you could rewind the universe to that first moment, you wouldn't find a spot where it all started. You'd find that every point in space was once at the center, including the point where you're sitting right now. That's hard to visualize. It's supposed to be. Human brains evolved to navigate environments where up and down mean something, where cause happens before effect, where things have edges. The early universe had none of that, but the math works. The equations describe it cleanly. And every observation we've made since the 1920s supports the conclusion that this is what happened. The framework for all of this came from Albert Einstein. In 1915, he published his general theory of relativity, a set of equations that describe how mass and energy warp the fabric of space and time. Gravity, in Einstein's model, is not a force pulling objects together. It's the curvature of space-time itself. A massive object, like a star, bends space around it the way a bowling ball would bend a stretched rubber sheet, and smaller objects roll along those curves. The equations were elegant, revolutionary, and they had an immediate problem. They didn't allow for a static universe. Einstein's equations predicted that space itself should be either expanding or contracting. A universe sitting still, unchanging and eternal, was not stable under general relativity. That bothered Einstein a lot. Because in 1915, everyone, including Einstein, assumed the universe was static. The Milky Way was thought to be the entire cosmos, and it didn't look like it was going anywhere. So Einstein did what any physicist would do when their beautiful theory conflicts with observed reality. He fudged it. He added a term to his equations called the cosmological constant, a kind of anti-gravity that would hold the universe in place, a mathematical thumb on the scale to keep everything from collapsing or flying apart. Then in 1922, a Russian mathematician named Alexander Friedmann took Einstein's original equations, the ones without the fudge factor, and worked out what they actually predicted. He found that the universe had to be dynamic. It had to be expanding or contracting, and if it was expanding, you could run the math backward and calculate how long it had been expanding. Friedmann's estimate came out to about 10 billion years. That was the first scientific attempt to calculate the age of the universe, and it came from taking Einstein's equations seriously in a way Einstein himself had refused to do. Einstein didn't like it. Friedmann sent him a copy of the paper. Einstein wrote back pointing out what he thought was a mathematical error. Friedmann checked. There was no error. Einstein eventually admitted the math was correct, but dismissed the result as physically meaningless. A curiosity, not a description of reality. He wasn't alone. Most physicists at the time ignored Friedmann's work completely. Then, in 1927, A Belgian priest and physicist named Georges Lemaitre, working independently, came to the same conclusion. Lemaitre went further. He proposed that if the universe was expanding, it must have been smaller in the past. And if you rewound far enough, it must have started from what he called a primeval atom, a single point containing all the mass and energy that would eventually become everything. Lemaitre presented his idea to Einstein at a conference in Brussels. Einstein listened, acknowledged that the mathematics were correct, and then told him, "Your calculations are accurate, but your physics is dreadful." That's a direct quote. Einstein thought the idea of an expanding universe that started from a single point was absurd. He held that position for years. It took observational evidence to change his mind, and that evidence came from an astronomer named Edwin Hubble. By the late 1920s, Hubble had measured the distances to several galaxies and noticed something strange. The farther away a galaxy was, the faster it appeared to be moving away from us. That relationship, now called Hubble's law, was exactly what you'd expect if space itself was expanding. Galaxies weren't flying through space. Space was stretching, and the galaxies were being carried along for the ride. Einstein visited Hubble at Mount Wilson Observatory in 1931, looked at the data, and admitted he'd been wrong. He later called the cosmological constant, the term he'd added to keep the universe static, the biggest blunder of his life. Whether he actually said that, or whether it's been embellished over the years, is debatable, but the sentiment fits. The universe was expanding, the equations had been right all along, and if the universe was expanding, it had a history, a beginning. Lemaitre's primeval atom eventually got a catchier name. In 1949, physicist Fred Hoyle was giving a radio interview on the BBC, explaining an alternative theory he favored called the steady-state model, where the universe had no beginning and just kept expanding forever, with new matter constantly being created to fill the gaps. Hoyle was dismissive of Lemaitre's idea, referring to it mockingly as this Big Bang notion. The name stuck. Hoyle spent the rest of his life opposing the theory he'd accidentally named, and he lost. The evidence piled up. The Big Bang won. So what actually happened in those first moments? The honest answer is, we don't know all of it. Our current understanding of physics breaks down at the very beginning. General relativity describes gravity beautifully at large scales, but it doesn't play nicely with quantum mechanics, the set of rules that governs the behavior of particles at the smallest scales. At the singularity, both sets of rules should apply, and they contradict each other. We need a theory of quantum gravity to describe what happened at time zero, and we don't have one yet. What we do have is a timeline that starts a tiny fraction of a second after the beginning and works forward from there. At about 10 to the negative 34 seconds after the Big Bang, something called cosmic inflation happened. This is one of the most important and least intuitive concepts in all of cosmology. Inflation was a period of exponential expansion where the universe grew faster than the speed of light. That sounds like it violates relativity, and it doesn't, because space itself was expanding. Nothing was moving through space faster than light. Space was just stretching, and it stretched so fast that a region smaller than an atom ballooned to something the size of a grapefruit in a time span so brief it makes a microsecond look like an eternity. Why did inflation happen? The leading theory involves something called a scalar field, a kind of energy that permeated space in the early universe. As that field decayed, it released enormous amounts of energy, driving the expansion. When inflation ended, that energy converted into particles, matter, radiation. Everything that would go on to form stars and galaxies and planets, and eventually you. Inflation solved several major problems in cosmology. It explained why the universe looks so uniform in all directions. It explained why space appears flat on large scales, and it made predictions that were later confirmed by observations of the cosmic microwave background. Inflation is still being tested. Scientists are still trying to figure out the details of how it worked, what drove it, and whether it's even the right explanation. But the basic picture, a brief period of insanely fast expansion in the first moments after the Big Bang, is now a core part of the Standard Model. After inflation, the universe was unimaginably hot. We're talking temperatures around 10 to the 32 Kelvin. That's a 1 followed by 32 zeros. At that temperature, matter as we know it couldn't exist. There were no atoms, no protons, no neutrons, not even quarks bound together into anything stable. What existed was a roiling soup of fundamental particles and energy, smashing into each other, annihilating, reforming, all of it happening faster than anything we have words for. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were not yet distinct. At those temperatures, they were unified into a single force. As the universe expanded and cooled, those forces began to separate. Gravity split off first, almost immediately. The strong force, which holds atomic nuclei together, separated next. Then the weak force, responsible for certain types of radioactive decay, split from electromagnetism. By the time the universe was about a trillionth of a second old, all four forces were operating independently the way they do today. Within the first 3 minutes, the temperature had dropped enough for quarks to bind together into protons and neutrons. Those protons and neutrons started fusing into the lightest atomic nuclei, hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, is one of the key pieces of evidence supporting the Big Bang theory. The ratios of hydrogen to helium to lithium that we observe in the universe today match almost exactly what the theory predicts should have been produced in those first few minutes. That's not a coincidence. That's the universe keeping receipts. But even after nuclei formed, the universe was still far too hot for atoms. Electrons couldn't stay bound to nuclei. They kept getting knocked loose by high-energy photons. The universe was opaque, a glowing fog where light couldn't travel more than a short distance before slamming into a free electron and scattering. Picture trying to see through a cloud lit from within. That's what the universe looked like for the next several 100,000 years. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to finally stick to nuclei. Hydrogen atoms formed. Helium atoms formed. For the first time, the universe became transparent. Photons that had been trapped, scattering endlessly through the fog, were suddenly free to travel. They've been traveling ever since. We call this moment recombination, which is a terrible name because it implies the electrons and nuclei were combined before, and they weren't, but the name stuck. Recombination is the single most important event in the observable history of the universe, at least from the perspective of anyone trying to measure cosmic time. It's the moment when the universe went from opaque to transparent. It's the moment when light could finally escape and carry information across space, and the light that was released at that moment is still out there. Stretched by billions of years of cosmic expansion, cooled from visible wavelengths down into the microwave range, but still there, still detectable, still carrying the fingerprints of what the universe looked like when it was 380,000 years old. That light is called the cosmic microwave background, and it is the single most important clue we have for figuring out how old the universe is, what it's made of, and how it's been evolving. It's the earliest snapshot we'll ever get, the universe's baby picture. Before recombination, the universe was opaque. We can't see further back than that with light. Any information from earlier times has to come from other sources: gravitational waves, neutrinos, mathematical models. But the cosmic microwave background is the edge of the visible universe in time. It's the furthest back we can look using photons, and everything we know about the age of the cosmos is built on top of what that light tells us. So here's where we are. The universe started from an incredibly hot, dense state 8 billion years ago. It expanded rapidly, cooled, and within the first few minutes, the basic building blocks of matter were forged. For the next few 100,000 years, it was a glowing fog, too hot for atoms to hold together. Then it cooled enough for atoms to form, and the fog cleared. Light escaped. That light has been traveling toward us ever since, carrying with it a record of what the universe looked like at the moment it became transparent. Everything we've talked about so far is backstory. Important backstory, but backstory nonetheless. The real work of measuring the universe's age begins with that light. The cosmic microwave background is not just evidence that the Big Bang happened. It's a tool, a map, a message written in radiation that tells us how old the universe is, how fast it's been expanding, what it's made of, and how its structure evolved from a nearly smooth fog into the web of galaxies we see today. And the fact that we can decode that message, that we've built instruments sensitive enough to read the tiny variations in temperature imprinted on radiation that's been traveling for more than 13 billion years, is one of the most absurd and beautiful achievements in the history of science. We'll get to how that works next, but before we do, take a moment to appreciate what we've just walked through. The universe had a beginning. We know when it was. We know what happened in the seconds, minutes, and millennia afterward. We know why it looks the way it does today. And we know all of this because a handful of scientists, most of them working in the 20th century, took Einstein's equations seriously, pointed telescopes at the sky, and refused to accept that the universe was unknowable. Human beings have been telling stories about creation for as long as language has existed. Most of those stories were beautiful. Some of them were profound. None of them were checkable. The Big Bang is different. It's not a story, it's a model, and every prediction it makes can be tested. The temperature of the cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies, the rate of expansion, all of it lines up. The universe is telling us its own origin story, and we've learned how to listen. We left off at the moment the universe became transparent. 380,000 years after the Big Bang, electrons finally stuck to protons, atoms formed, and light that had been trapped in an endless game of pinball with free particles was suddenly free to travel. That light is still out there, cooled, stretched, dimmed by more than 13 billion years of cosmic expansion, but still there, still carrying information, still whispering the story of what the universe looked like when it was a baby. That light is the cosmic microwave background. And if you want to understand how we know the universe is 8 billion years old, you need to understand what the cosmic microwave background is, how we found it, and what it's telling us. Let's start with what it is, because the name itself is misleading. Cosmic microwave background sounds like something you'd need a PhD to care about. What it actually is the afterglow of creation, the earliest light in the universe, the farthest thing we can see in any direction. A faint hum of radiation filling every cubic meter of space, left over from the moment the cosmos went from opaque to transparent. It is, in the most literal sense, an echo, not of sound but of heat. the cooled remnant of a fireball that once filled the entire universe. Before recombination, the universe was a glowing fog. Photons couldn't travel more than a short distance before smacking into a free electron and scattering in a random direction. It was like trying to see through a cloud lit from the inside. Bright, yes, but you couldn't see through it. You couldn't see anything. There was no such thing as a clear line of sight because space itself was opaque. If you could somehow have been there, floating in that fog with eyes that could survive being vaporized, you wouldn't have seen stars or galaxies or even distant walls of light. You would have seen nothing but a uniform glow in every direction, like being inside a light bulb. Then the temperature dropped below about 3000 Kelvin. Electrons lost enough energy that they could finally be captured by protons and helium nuclei. Neutral atoms formed, hydrogen, helium, and with no more free electrons to scatter off of, photons were free to go. They stopped bouncing, they started traveling. And they've been traveling in straight lines ever since. That moment, that transition from fog to clarity, is called the epoch of recombination. Terrible name, as I mentioned earlier, because nothing was recombining. It was combining for the first time, but the name stuck, and now we're stuck with it. What matters is what happened next. The photons that were released at recombination have been streaming through space for more than 13 billion years. As the universe expanded, those photons got stretched along with everything else. Their wavelengths grew longer. Their energy dropped. They started as visible light, glowing orange and red like the surface of a cool star. By now, they've been stretched so much that they've shifted all the way into the microwave part of the spectrum, invisible to the human eye, invisible to most instruments, but detectable if you know where to look and what you're looking for. The cosmic microwave background is not coming from a specific place. It's coming from everywhere. Every point in space is receiving this radiation from every direction. It fills the universe the way air fills a room. You can't point a telescope at the cosmic microwave background and say it's over there. It's here, it's there, it's everywhere. The entire sky glows faintly in microwaves, and that glow is the cooled light of the early universe, still washing over us 13.8 billion years later. That makes it the oldest thing we can see. Not the oldest object, the oldest light, the farthest back in time we can look using photons. Before recombination, the universe was opaque. We can't see past that wall. The cosmic microwave background is the edge, the horizon. The baby picture of the cosmos, frozen at 380,000 years old and delivered to our instruments after a journey lasting nearly the entire age of the universe. The temperature of that radiation today is 272,548 Kelvin. That's about minus 270 degrees Celsius, just a few degrees above absolute zero. To put that in perspective, the coldest natural place on Earth, in the heart of Antarctica, in the dead of winter, gets down to around minus 90 Celsius. The cosmic microwave background is 3 times colder than that. It's cold because the universe has been expanding for 13.8 billion years, and expansion cools things down. Stretch a hot gas and it gets cooler. Stretch the fabric of space itself and the radiation moving through it gets cooler. The cosmic microwave background started hot. Now it's one of the coldest things in the universe. The story of how we found it is one of the best accidents in the history of science. In 1948, a physicist named Ralph Alpha, working with George Gamow and Robert Herman, was studying what would have happened in the early universe if the Big Bang theory was correct. They calculated that the intense heat from the early universe should have left behind a faint glow of radiation, cooled by billions of years of expansion. They predicted a temperature of around 5 Kelvin, close. Not exact, but close enough that if anyone had taken them seriously and gone looking, they might have found it. Nobody went looking. The prediction was published, it was noted, and then it was largely ignored for nearly 2 decades. Partly because measuring something that cold and that faint with 1940s technology was somewhere between extremely difficult and impossible. Partly because the Big Bang theory itself was still controversial. A lot of physicists in the 1950s preferred the steady-state model, which said the universe had no beginning and just kept going forever. If the universe didn't start with a bang, there'd be no afterglow to find. So why look? Then in 1964, 2 radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to get a very sensitive radio antenna to work properly. The antenna had been built for satellite communication, but Bell Labs had repurposed it for radio astronomy. Penzias and Wilson wanted to use it to study faint radio signals from the Milky Way. They pointed the antenna at the sky. They started taking measurements, and they kept picking up noise, a persistent hiss coming from every direction. It didn't matter where they pointed the antenna. It didn't matter what time of day it was. The noise was always there. Same intensity, same frequency, coming from everywhere. At first, they thought it was interference, maybe from New York City, which was relatively close. But the signal didn't change when they pointed away from the city. Then they thought it might be the antenna itself. Maybe something inside it was generating heat and radiating at microwave frequencies. They checked. They found pigeon droppings caked inside the antenna. Pigeons had been nesting in there. Penzias and Wilson cleaned out the droppings, which they later described in much more polite terms in their published paper, and tested the antenna again. The noise was still there, same strength, same everywhere. They tested the equipment. They checked for electrical interference. They ruled out the sun, the moon, the Earth, the galaxy. Nothing they tried made the signal go away. It was real. It was coming from outside the Milky Way, and it was coming from every direction at once with exactly the same intensity. That shouldn't be possible unless the source was the entire universe. Around the same time, a team of physicists at Princeton University, led by Robert Dicke, was building an instrument specifically designed to search for the cosmic microwave background. They'd read Alpha's old prediction and decided it was worth testing. They were about to start observations when Dicke got a phone call from Penzias. Penzias explained what he and Wilson had been seeing and asked if Dicke had any idea what it might be. Dicke listened, hung up, turned to his team and said, "Well, boys, we've been scooped." Penzias and Wilson hadn't been looking for the cosmic microwave background. They didn't even know it was supposed to exist. They'd stumbled into the most important cosmological discovery of the 20th century while trying to get rid of noise in a radio telescope. Their paper, published in 1965, was dry, cautious, and avoided any grand claims about the origin of the universe. A companion paper by Dicke's team, published in the same journal issue, laid out the cosmological interpretation. The signal Penzias and Wilson had detected was the cooled radiation from the Big Bang, the afterglow of creation, the smoking gun. Most astronomers who'd been skeptical of the Big Bang theory changed their minds within a few years. The cosmic microwave background was exactly what the theory predicted. The steady-state model had no good explanation for it. You can argue about a lot of things in cosmology. You can't argue with a signal that strong, that uniform, coming from every direction in space. The Big Bang won. Penzias and Wilson shared the Nobel Prize in Physics in 1978. Alpha and Herman, who'd predicted the cosmic microwave background 30 years earlier, were passed over. Science is not always fair about credit. Discovering the cosmic microwave background was a breakthrough. Measuring it carefully enough to extract useful information took decades. The first measurements confirmed it existed and gave a rough temperature. But the real power of the cosmic microwave background comes from its tiny imperfections. The radiation is not perfectly uniform. It's close, incredibly close. The temperature varies by only about 1 part in 25,000 from one part of the sky to another. But those variations, those tiny ripples in temperature, contain more information about the early universe than anything else we've ever measured. They are the seeds of structure, the blueprints for galaxies, a fossilized map of the universe as it existed 380,000 years after the Big Bang. To see those ripples, you need instruments far more sensitive than anything available in the 1960s. You need to measure temperature differences of a few millionths of a Kelvin across the sky. You need to filter out interference from Earth's atmosphere, from the Sun, from the Milky Way, from radio broadcasts, from every source of microwave radiation that isn't the cosmic microwave background. And you need to do all of that while floating in space where the environment is cold and stable enough that your detectors don't drown in their own heat. NASA launched the Cosmic Background Explorer satellite, COBE, in 1989. It carried 3 instruments designed to study the cosmic microwave background in unprecedented detail. One of those instruments, FIRAS, measured the spectrum of the radiation with exquisite precision. The result was a nearly perfect black body curve, the kind of curve you get from an object that's in perfect thermal equilibrium, radiating at a single well-defined temperature. The fit was so precise that it's still one of the most accurate measurements in all of physics. The cosmic microwave background is a black body spectrum at 273 Kelvin, not approximately, exactly. The second instrument, DMR, mapped the full sky and measured the temperature variations. In 1992, the COBE team released the first full sky map of the cosmic microwave background's anisotropies. The image showed a mottled pattern of slightly warmer and slightly cooler regions spread across the sky. The temperature differences were tiny, only about 100 microkelvin, but they were real, and they were exactly the kind of pattern you'd expect if the early universe had contained small density fluctuations that would later collapse under gravity to form galaxies. The announcement made headlines. George Smoot, the lead scientist on the DMR instrument, described the image as seeing the face of God. That was probably overselling it, but the discovery was profound. The cosmic microwave background wasn't just proof that the Big Bang happened, it was a map, a snapshot of the universe at 380,000 years old, showing the distribution of matter and energy at a time when the cosmos was still smooth and simple. The ripples COBE detected were the ancestors of every galaxy, every star, every planet that exists today. They were the beginning of structure, and they'd been frozen into the cosmic microwave background for more than 13 billion years, waiting for someone to build an instrument sensitive enough to see them. COBE's map was blurry. Its resolution was low. It could see the largest ripples, but the smaller details were invisible. NASA followed up with a more advanced mission in 2001, the Wilkinson Microwave Anisotropy Probe, WMAP, which spent 9 years mapping the cosmic microwave background with far higher resolution and sensitivity. WMAP's maps revealed structure on smaller scales. The ripples had substructure. There were patterns within patterns. By analyzing those patterns, cosmologists could extract the fundamental parameters of the universe: how old it is, how fast it's expanding, what it's made of, the proportions of ordinary matter, and dark energy. All of that information was encoded in the shape and size of the ripples. WMAP's first results, released in 2003, gave an age of 13, 7 billion years with an uncertainty of about 200 million years. That was the most precise estimate anyone had ever published, and it came directly from analyzing the cosmic microwave background. By the time WMAP finished taking data in 2010, the uncertainty had shrunk even further. The universe was 77 billion years old, plus or minus 59 million years. That's an error bar of less than 0.5%. For a measurement spanning the entire history of the cosmos, that's absurd. Then the European Space Agency launched Planck in 2009. Planck was the most sensitive instrument ever built to study the cosmic microwave background. It mapped the sky at 9 different frequencies, each one chosen to cut through different kinds of foreground contamination. It measured temperature differences down to a few millionths of a Kelvin. And it produced the most detailed map of the early universe we've ever seen. Planck's final results, released in 2018, gave an age of 798 billion years, plus or minus 37 million years. That's the number we use today, 8 billion years. The uncertainty is so small, it barely matters for most practical purposes. And every bit of that precision came from studying a faint glow of radiation that's been traveling toward us since the universe was 380,000 years old. Here's what makes this so powerful. The cosmic microwave background is not just evidence that the Big Bang happened. It's a laboratory. The tiny temperature variations across the sky encode information about the density, composition, and geometry of the early universe. By measuring how large those variations are and how they're distributed across different angular scales, you can calculate how much ordinary matter the universe contains, how much dark matter, how much dark energy. You can measure the curvature of space. You can determine the rate of expansion, both today and in the past. You can test whether the laws of physics were the same 13 billion years ago as they are now. All of that from a map of temperature ripples in a bath of microwave radiation filling the sky. It's one of the most extraordinary tools science has ever built, and it exists because the universe became transparent at a specific moment in its history, and the light from that moment is still reaching us today. The cosmic microwave background is uniform to about 1 part in 25,000. That means if you pick 2 random points on opposite sides of the sky and measure the temperature of the radiation coming from each, the temperatures will agree to within 0.4%. That's absurdly smooth, and it's one of the reasons inflation was proposed. Without inflation, there's no good explanation for why regions of the universe that were never in contact with each other, that were too far apart for light to have ever traveled between them, should have exactly the same temperature. Inflation solves that by proposing that those regions were once close together, came into thermal equilibrium, and then got stretched apart faster than light during the inflationary period. The smoothness of the cosmic microwave background is evidence that inflation happened. The ripples, the tiny deviations from perfect smoothness, are evidence that the early universe wasn't completely uniform. There were small fluctuations in density, regions that were slightly denser than average. Those regions had slightly stronger gravity. They pulled in more matter. Over time, they collapsed into the first stars, the first galaxies, the first clusters of galaxies. The cosmic microwave background shows us those fluctuations when they were tiny, a few parts in 100,000, before anything had collapsed, before structure had formed. The universe at that moment was still an almost perfectly smooth gas of hydrogen and helium, glowing faintly as it cooled. But the seeds were already there, written into the fabric of space in the form of tiny ripples in temperature and density. When you look at a map of the cosmic microwave background, what you're seeing is the blueprint for everything that came after. Every galaxy cluster, every void, every filament of the cosmic web can trace its ancestry back to one of those ripples. The structure of the universe today is just the amplified, collapsed, evolved version of the structure that was already present at 380,000 years. The cosmic microwave background froze that early structure in place like a photograph, and we've been studying that photograph for 30 years, trying to extract every bit of information it contains. There's one more thing the cosmic microwave background gives us, and it's the thing that matters most for this video. Time. The age of the universe. By measuring the temperature of the radiation, the size and distribution of the ripples, and the overall geometry of space, you can run the equations of the Standard Model backward and calculate how long the universe has been expanding. You can determine the rate of expansion at different times in the past. You can account for the effects of dark matter and dark energy. You can build a timeline. And every independent method we have for measuring the age of the universe, every technique that doesn't rely on the cosmic microwave background, gives an answer that's close to what the cosmic microwave background says. The oldest stars we've found are about 13 billion years old, maybe a little older, which fits perfectly. The distances to faraway galaxies, measured using supernova, give expansion rates that, when run backward, point to an origin roughly 13 to 14 billion years ago. The abundances of hydrogen and helium and lithium in the universe match what you'd expect if the Big Bang happened about 8 billion years ago. Every piece of evidence points the same direction. The cosmic microwave background is the anchor. It's the measurement everything else is checked against. Because, unlike stars, which can be hard to date precisely, or galaxies which are complicated and messy, the cosmic microwave background is simple. It's thermal radiation from a well-understood physical process. The math is clean. The predictions are testable. And the agreement between theory and observation is so tight that it leaves almost no room for error. So when someone tells you the universe is 8 billion years old, what they're really telling you is that the cosmic microwave background, the cooled afterglow of the moment the universe became transparent, has been traveling toward us for that long. The light we're detecting today left its source when the universe was 380,000 years old. It's been stretched by expansion, cooled to just under 3 Kelvin, and spread uniformly across the entire sky. And embedded in that light, in the tiny temperature variations from one patch of sky to another, is a record of the early universe detailed enough that we can reconstruct its history, measure its age, and predict its future. The cosmic microwave background is the universe's baby picture. And like any good photograph, it tells you more the longer you look at it. We've covered the cosmic microwave background, that faint hum of radiation filling the universe, the afterglow left over from when the cosmos first became transparent. We've talked about how it gives us a snapshot of the universe at 380,000 years old, and how analyzing the tiny temperature ripples across the sky lets physicists calculate the age, composition, and expansion rate of everything that exists. That's one method. It's powerful, it's precise, and it's relatively new. For most of the 20th century, cosmologists didn't have satellites mapping microwave radiation across the sky. They had telescopes pointed at stars. And if they wanted to know how old the universe was, they first had to figure out how big it was, which meant they needed to measure distances, not distances across town or across continents. Distances to objects so far away that their light takes millions or billions of years to reach us. That's a different problem entirely. You can't use a tape measure, you can't send a probe, you can't triangulate in any conventional sense once you get past a certain range. What you can do, if you're clever, is find objects out there whose intrinsic brightness you know, objects that shine with a predictable luminosity. If you know how bright something truly is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. The math is straightforward. The challenge is finding objects reliable enough to trust. Astronomers call these objects standard candles, and they are the backbone of cosmic distance measurement. Without them, we'd have no idea how far away most galaxies are. We wouldn't know how fast the universe is expanding. We couldn't calculate its age. The entire framework of modern cosmology rests on the assumption that certain kinds of stars and explosions shine with consistent, measurable brightness. Get that assumption wrong, and everything downstream collapses. Get it right, and you can map the universe. Let's start with the simplest method, because it's the one that stops working almost immediately: parallax. If you hold your thumb up at arm's length and close one eye, then switch eyes, your thumb appears to shift position against the background. That shift is parallax. The closer your thumb is to your face, the bigger the shift. The farther away, the smaller. If you know the distance between your eyes and you measure the angle of the shift, you can calculate how far away your thumb is. Basic trigonometry. Astronomers use the same trick with stars. As Earth orbits the Sun, our perspective shifts. A nearby star will appear to move slightly against the background of more distant stars. Measure that tiny shift, and you can calculate the star's distance. The method works beautifully for stars within a few hundred light years. Beyond that, the angles get too small. Even the best telescopes struggle to measure shifts smaller than a few thousandths of an arcsecond. At distances beyond about 10,000 light-years, parallax becomes unreliable. And the universe is much, much larger than 10,000 light-years. The Milky Way is about 100,000 light-years across. The nearest large galaxy, Andromeda, is 5 million light-years away. The edge of the observable universe is more than 46 billion light-years from here. Parallax gets you nowhere near the distances that matter for cosmology. So astronomers needed something else. They needed objects whose brightness they could trust without having to measure their distance first. They needed standard candles. The first real breakthrough came in the early 1900s, and it came from a woman who wasn't allowed to operate a telescope. Henrietta Swan Leavitt worked at the Harvard College Observatory starting in 1893. Her official title was computer, not the electronic kind, the human kind. Leavitt's job was to examine photographic plates, glass images of the night sky, and catalogue the brightness of stars. It was tedious work. It paid poorly, and Leavitt was better at it than almost anyone. She focused on a class of stars called Cepheid variables. These stars pulse. Their brightness rises and falls in a regular cycle, like a slow heartbeat. Some Cepheids complete a cycle in a few days, others take weeks. Leavitt was studying Cepheids in the Small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. The advantage of looking at stars in another galaxy is that they're all roughly the same distance from Earth. If one Cepheid looks brighter than another, it's because it actually is brighter, not because it's closer. Leavitt noticed something. The Cepheids with longer periods, the ones that took more days to complete a cycle, were brighter than the ones with shorter periods. Not just a little brighter, predictably brighter. There was a direct relationship between how long a Cepheid's period was and how luminous it actually was. She published her findings between 1908 and 1912. The discovery didn't make headlines. Leavitt was credited in the papers, but she wasn't celebrated. She went back to cataloguing stars. She died in 1921 from cancer, largely unknown outside a small circle of astronomers. What Leavitt had discovered was the first standard candle. If you measure how long it takes a Cepheid to go through one cycle of brightening and dimming, you can calculate its true luminosity. Once you know its true luminosity, you compare that to how bright it looks from Earth, and the difference tells you how far away it is. Cepheids became cosmic measuring sticks. Within a decade, astronomers were using them to measure distances to other galaxies, proving for the first time that the Milky Way was not the entire universe. N.R. Hertzsprung calibrated Leavitt's period luminosity relationship in 1913 by measuring the distances to nearby Cepheids using parallax. Once that calibration was set, every other Cepheid in the sky became a distance marker. Edwin Hubble used Cepheids in the 1920s to measure the distance to Andromeda and prove it was a separate galaxy, millions of light-years away. That was the observation that broke open cosmology. Without Leavitt's work, Hubble couldn't have done it. Cepheids are still used today. The Hubble Space Telescope has observed Cepheids in galaxies up to about 100 million light-years away. That's far enough to measure the local expansion rate of the universe with high precision. But 100 million light-years is nothing on cosmic scales. To measure distances to galaxies billions of light-years away, to probe the deep history of the universe's expansion, astronomers needed something brighter, something that could be seen across a significant fraction of the observable universe. They needed supernovae. Not just any supernova, a specific kind, Type 1a. When a massive star runs out of fuel and collapses, it explodes in what's called a core collapse supernova. These are dramatic, violent, and extremely bright. They're also inconsistent. Different stars explode with different energies depending on their mass, composition, and rotation. You can't use them as standard candles because their brightness varies too much. Type 1, a supernovae, are different. They don't come from massive stars, they come from white dwarfs, the dense remnants left behind after a sun-like star dies. A white dwarf is stable on its own. It's held up by electron degeneracy pressure, a quantum mechanical effect that keeps it from collapsing under its own gravity. But if that white dwarf has a companion star and starts pulling matter off of it, the white dwarf's mass increases. Once it reaches a critical threshold, about 1/4 times the mass of the Sun, a limit called the Chandrasekhar limit, the core can no longer support itself. It collapses. The collapse triggers runaway fusion. Carbon and oxygen in the core fuse into heavier elements in a chain reaction that takes less than a second. The entire white dwarf explodes. Nothing is left behind, no remnant, just an expanding cloud of debris and a burst of light bright enough to outshine an entire galaxy. The key is that every Type 1 supernova explodes at roughly the same mass. That means they all release roughly the same amount of energy. They all reach roughly the same peak brightness. At their brightest, a Type 1 supernova shines with a luminosity of about 4 billion times the Sun. You can see that from halfway across the observable universe. They are, in the words of one astronomer, superb distance indicators. They're not perfectly uniform. Some Type 1 supernovae are a bit brighter than others. Some fade faster. But astronomers figured out how to correct for that. By measuring the shape of the supernova's light curve, how quickly it brightens and how quickly it fades, you can standardize its peak luminosity. Brighter ones fade slower, dimmer ones fade faster. Once you apply that correction, Type 1 supernovae become remarkably consistent. Consistent enough to measure distances across billions of light-years with uncertainties of just a few percent. In the 1990s, 2 independent teams used Type 1 supernovae to measure the expansion history of the universe. They weren't trying to calculate the age of the cosmos. They were trying to figure out whether the expansion was slowing down. The assumption at the time was that gravity should be pulling everything back together, gradually slowing the rate at which galaxies are moving apart. The question was how much. The answer, when it came, was none. The expansion wasn't slowing down, it was speeding up. That discovery won the 2011 Nobel Prize in Physics, and it forced cosmologists to add a completely new component to their models: dark energy, a mysterious force that pushes space apart, counteracting gravity and driving the universe's accelerating expansion. Without Type 1, a supernovae, we wouldn't know dark energy exists. Without dark energy, the calculated age of the universe would be wrong. The cosmic microwave background gives you one number. Supernovae give you another. They have to agree. And they mostly do, though the tension between the two methods has been growing in recent years. We'll come back to that. The process of using standard candles to measure cosmic distances is called the distance ladder, and the name is literal. You start with the bottom rung, parallax for nearby stars. Then you use those nearby stars to calibrate the next rung, Cepheid variables. You use Cepheids to calibrate the rung above that. Type 1, a supernovae. Each step depends on the one before it. If you get the calibration wrong at any level, the error propagates upward, and every distance measurement beyond that point is off. Henrietta Leavitt's period luminosity relationship is one of those rungs. To use Cepheids as standard candles, you first have to calibrate their absolute brightness. Leavitt identified the relationship, but she didn't have the distances to any Cepheids, so she couldn't set the scale. Edgar Hertzsprung did that by measuring parallaxes to a handful of nearby Cepheids. That gave him their distances. Once he knew their distances and their apparent brightness, he could calculate their true luminosity. That locked in the period luminosity relationship. Every Cepheid after that could be measured using the same scale, except the early calibrations were wrong. The distances Hertzsprung used were off. That mistake propagated upward. When Edwin Hubble used Cepheids to measure the distance to other galaxies in the 1920s, he underestimated those distances by a factor of about 7. That made the universe look smaller than it was. It also made the expansion rate look faster than it was, which in turn made the calculated age of the universe come out absurdly young. Hubble's initial estimate put the age of the universe at less than 2 billion years. Geologists already knew Earth was older than that. The numbers didn't work. It took decades to figure out why. The problem was identified in the 1950s by Walter Baade, an astronomer at Mount Wilson Observatory. Baade realized there were two types of Cepheid variables with different period luminosity relationships. Hubble had been using the wrong relationship for the Cepheids he observed in other galaxies. Once the correction was applied, the distances doubled, the expansion rate dropped, the age of the universe increased. Suddenly, the numbers made sense again. The universe was older than Earth. Crisis averted. This is why calibration matters. Standard candles are only useful if you know exactly how bright they are. That requires measuring the distances to at least a few of them using an independent method. Parallax works for the nearest ones, but parallax has limits. Even with the European Space Agency's Gaia satellite, which has measured parallaxes for more than 1 billion stars with unprecedented precision, the method only reaches out to a few tens of thousands of light years. Beyond that, you're relying on models, assumptions, and cross-checks against other types of stars. Cepheids aren't the only game in town, by the way. Astronomers use several other types of objects as distance indicators. RR Lyra stars, which are similar to Cepheids but older and dimmer, can be used to measure distances within the Milky Way and nearby galaxies. Red giant stars have a predictable maximum brightness, called the tip of the red giant branch, that can be used as a distance marker. Certain types of eclipsing binary stars can be analyzed to extract both their size and their luminosity, giving you another independent distance measurement. Each method has its own strengths, its own uncertainties, and its own range of applicability. The real power comes from combining them. If you measure the distance to a galaxy using Cephids and get one number, then measure it using the tip of the red giant branch and get the same number. You can be reasonably confident the distance is correct. If the numbers disagree, something is wrong. Either the calibration is off, or there's dust blocking the light and making things look dimmer than they are, or one of your assumptions doesn't hold. Distance measurement in astronomy is not a single technique, it's a web of cross-checks, each method validating the others. Type 1, a supernovae, sit at the top of that ladder because they're bright enough to be seen at cosmological distances. But you can't use them to measure distances unless you've first calibrated their absolute brightness. And you can't calibrate them unless you've measured the distances to a few nearby galaxies where Type 1 a supernovae have exploded. Those distances come from Cephids, which means the accuracy of every distance measurement made using supernovae depends on the accuracy of Leavitt's period luminosity relationship, which depends on the accuracy of the parallax measurements used to calibrate the nearest Cephids, which depends on the precision of the telescopes doing the measuring. Everything is connected. The Hubble Space Telescope spent years observing Cephids in distant galaxies, specifically to improve the calibration of the distance ladder. Adam Rees and his team have been refining those measurements for more than 2 decades, pushing the range of observable Cephids further and reducing the uncertainties at every step. The James Webb Space Telescope, with its larger mirror and better infrared sensitivity, is now picking up where Hubble left off, observing Cephids in galaxies where Hubble's images were crowded and blurry. Every new observation tightens the error bars. Every refinement brings the calculated expansion rate closer to the true value, or so the hope goes. Because here's the uncomfortable part. The more precise the measurements get, the more obvious it becomes that something doesn't quite add up. The expansion rate calculated using the distance ladder, starting with parallax and climbing up through Cephids and supernova, gives a number around 73 kilometers per second per megaparsec. The expansion rate, calculated from the cosmic microwave background, using the physics of the early universe and projecting forward, gives a number around 67. That's a gap of roughly 9%. It's persistent. It's not going away. And it's one of the most important unsolved problems in cosmology right now. Both methods depend on standard candles in different ways. The cosmic microwave background analysis doesn't use Cephids or supernovae directly, but it does rely on models of how structure formed in the early universe. Those models assume certain things about dark matter and dark energy. The distance ladder, on the other hand, is built from direct observations of stars and explosions. It's empirical. It's grounded in objects we can see and measure. If the two methods disagree, either the observations are wrong, or the models are wrong, or something about the universe is more complicated than we've accounted for. Some astronomers think the tension will resolve itself with better data. Maybe there's a systematic error in the Cephid calibrations. Maybe dust is dimming distant supernovae more than expected. Maybe the tip of the red giant branch isn't as uniform as we thought. Others think the tension is real, that the universe is telling us something and we need to listen. Maybe dark energy behaves differently than our models predict. Maybe the expansion rate has changed in ways we haven't accounted for. Maybe the standard model of cosmology is incomplete. Standard candles are not infallible. They're called standard because they're consistent, not because they're perfect. Cepheids vary in brightness depending on their metallicity, the abundance of elements heavier than helium in their atmospheres. Dust between us and a distant star can absorb and scatter light, making the star look dimmer and therefore farther away than it really is. Type 1, a supernovae, despite their uniformity, still shows some scatter in peak brightness even after corrections are applied. Every standard candle comes with uncertainties. The question is whether those uncertainties are large enough to explain the tension, or whether something deeper is going on. For now, the distance ladder works. It's gotten us this far. We know the universe is expanding. We know roughly how fast. We know the distances to thousands of galaxies. We've mapped the large-scale structure of the cosmos out to billions of light years. All of that rests on the assumption that certain objects shine with predictable brightness, and that assumption has held up under decades of scrutiny. Leavitt's period luminosity relationship still works. Type 1, a supernovae, still explode at the Chandrasekhar limit. The physics hasn't changed. What has changed is the precision. When Hubble first measured the expansion rate in 1929, his number was off by a factor of 7. By the 1970s, astronomers had narrowed it down to somewhere between 50 and 100. By the 1990s, the range was 60 to 80. Today, depending on which method you use, the answer is either 67 or 73, and the error bars have shrunk so much that the two values no longer overlap. That's progress. Frustrating progress, but progress nonetheless. The universe is not hiding from us. It's broadcasting its properties in every direction. The light from distant stars carries information about their distance, their composition, their motion. The challenge is learning how to read that light correctly. Standard candles are the key to that reading. They're the objects whose brightness we can trust, whose distances we can calculate, whose motion tells us how fast space itself is stretching. Without them, cosmology would still be guesswork. With them, it's a science. And now that we've covered how astronomers measure distances, we can move on to what those distances tell us. Because once you know how far away a galaxy is, you can measure how fast it's moving. And once you measure how fast galaxies at different distances are moving, you start to see a pattern. A relationship between distance and velocity that reveals something profound about the nature of space itself. That's where we're going next. We've established that certain stars and explosions shine with predictable brightness, and that by measuring how bright they appear versus how bright they truly are, we can calculate their distance. That's the distance ladder. Parallax for nearby stars, Cepheids for intermediate distances, Type 1 a supernovae for the truly remote corners of the universe. It works. It's been working for a century. And it gave astronomers something they'd never had before, the ability to measure how far away galaxies actually are. But distance by itself doesn't tell you much. A galaxy sitting 10 million light-years away is interesting, sure. A data point, a dot on a map. What matters is what that galaxy is doing. Is it sitting still? Is it moving toward us, away from us? How fast? And if you measure enough galaxies, if you plot their distances against their velocities, do you see a pattern? Or is the universe just chaos, galaxies drifting randomly through space like leaves in a pond? The answer came in 1929, and it changed everything. But to understand what Edwin Hubble discovered and why it mattered, you need to understand the clue that made the discovery possible: redshift. The stretching of light itself as it travels through expanding space. The single most important observational tool in all of cosmology, and one that almost no one outside the field actually understands. Let's start with something simpler: sound. You've experienced this 1,000 times without thinking about it. An ambulance drives toward you, siren blaring. The pitch is high. Then it passes, and the pitch drops. Lower, noticeably lower. The siren itself hasn't changed. The sound it's producing is the same frequency it was producing the whole time. What changed is your relationship to it. When the ambulance was moving toward you, each sound wave was emitted from a slightly closer position than the one before. The waves got bunched up, compressed. That compression made the frequency higher and the pitch rise. When the ambulance moved away, the opposite happened. Each wave was emitted from slightly farther away. The waves stretched out, the frequency dropped, the pitch fell. That's the Doppler effect, named after Christian Doppler, an Austrian physicist who described it mathematically in 1842. It applies to any wave, sound, water, light. If the source is moving toward you, the waves get compressed and the frequency goes up. If the source is moving away, the waves stretch and the frequency drops. For sound, we hear that as a change in pitch. For light, we see it as a change in color. Light is an electromagnetic wave. It has a frequency and a wavelength. Blue light has a shorter wavelength and a higher frequency. Red light has a longer wavelength and a lower frequency. If a source of light is moving toward you, the light waves get compressed. The wavelength shortens. The light shifts toward the blue end of the spectrum. We call that blue shift. If the source is moving away, the waves stretch, the wavelength lengthens, the light shifts toward red. That's redshift. You don't notice this in everyday life because the speeds involved are too slow. A car driving toward you with its headlights on is not moving fast enough to produce a measurable shift in the color of the light. You'd need the car to be moving at a significant fraction of the speed of light before your eyes could detect the change. But stars and galaxies don't care what your eyes can detect. They're moving. And if you have the right instruments, you can measure how fast they're moving by analyzing the light they emit. Stars don't produce light at a single wavelength. They produce a spectrum, a continuous range of wavelengths that when spread out with a prism or a diffraction grating looks like a rainbow. But that rainbow isn't smooth. It has dark lines in it, gaps, absorption lines. Those lines are caused by specific atoms in the star's atmosphere absorbing light at very specific wavelengths. Hydrogen absorbs at certain wavelengths, helium at others, calcium, iron, sodium. Every element has its own unique fingerprint. The key is that those absorption lines always appear at the same wavelengths if the source is sitting still relative to you. Hydrogen's lines are always in the same place, always, unless the source is moving. If the star is moving toward you, the entire spectrum shifts toward shorter wavelengths. Every absorption line moves toward the blue end. If the star is moving away, the lines shift toward red. By measuring how far the lines have shifted, you can calculate how fast the star is moving along your line of sight, not its total velocity, just the component moving toward or away from you. This technique, called spectroscopy, became one of the most powerful tools in astronomy by the late 19th century. Point a telescope at a star, split its light into a spectrum, identify the absorption lines, measure how far they've shifted from their rest positions, calculate the velocity. Simple in principle, difficult in practice. The shifts are tiny. You need precise instruments. You need long exposures. You need clear skies and stable equipment and a lot of patience. The first person to apply this technique to galaxies systematically was an astronomer named Vesto Slipher. You've probably never heard of him. Most people haven't. He worked at Lowell Observatory in Flagstaff, Arizona, starting in 1901, and he spent years taking spectra of what were then called spiral nebulae. At the time, no one knew whether these nebulae were clouds of gas inside the Milky Way or separate galaxies far beyond it. That debate wouldn't be settled until the 1920s. Slipher wasn't trying to resolve that question. He was just measuring velocities. He started in 1912 with the Andromeda Nebula. Getting a clean spectrum was hard. The nebula was faint. Slipher had to expose his photographic plates for hours, sometimes over multiple nights, to collect enough light. When he finally analyzed the spectrum, he found that Andromeda's absorption lines were shifted toward the blue. The entire nebula was moving toward us at about 300 kilometers per second. That was shockingly fast, faster than any star in the Milky Way had ever been measured moving. It suggested Andromeda might not be part of the Milky Way at all. Slipher kept going. He measured more spiral nebulae. Most of them were redshifted. They were moving away, and some of them were moving away fast. By 1914, he'd measured the velocities of 15 nebulae. 13 were redshifted. Only 2, including Andromeda, were blue-shifted. By 1925, Slipher had velocities for 45 nebulae. The vast majority were receding, some at speeds exceeding 1,000 kilometers per second. Slipher didn't know what to make of it. He reported his findings at conferences and published them in journals. Other astronomers noticed. One of them was Georges Lemaitre, the Belgian priest and physicist who'd independently derived the equations predicting an expanding universe. Lemaitre read Slipher's papers and realized the redshifts weren't random. They fit a pattern. In 1927, Lemaitre published a paper proposing that the universe was expanding and that the velocities of these nebulae were proportional to their distances. He even calculated an approximate rate of expansion. His estimate was close to what we know today, and almost no one paid attention. Lemaitre's paper was published in French in a Belgian journal with limited circulation. It didn't get translated into English until 1931, and by then someone else had already gotten the credit. That someone was Edwin Hubble. Hubble didn't measure any of the velocities himself. He used Slipher's data. What Hubble contributed was the other half of the equation: distance. By the late 1920s, Hubble had measured the distances to about 24 galaxies using Cepheid variables. He had access to the 100-inch Hooker telescope at Mount Wilson Observatory, the largest and most powerful telescope in the world at that time. He used it to resolve individual stars in nearby galaxies, identify Cepheids, measure their periods, and calculate their distances. Once he had those distances, he compared them to Slipher's redshift measurements, and there it was, a relationship, a trend. The farther away a galaxy was, the faster it was moving away from us. Hubble published his results in 1929 in a paper that ran just 6 pages. The data were messy, the distances were rough, the velocities were scattered, but the trend was clear. Plot distance on one axis and velocity on the other, and the points fell along a line, a straight line. The slope of that line was the rate of expansion. Hubble called it the expansion rate. Today we call it the Hubble constant, though Hubble himself didn't call it that, and the name has caused no end of confusion because the constant isn't actually constant. It changes over time as the universe evolves. But in 1929, none of that was clear yet. What was clear was the implication. If galaxies were moving away from us, and the farther away they were, the faster they were receding, then the universe was expanding, not just changing, expanding. Space itself was stretching, carrying galaxies along for the ride. Run the math backward, and you could calculate how long the universe had been expanding. Hubble's original estimate, based on his distances and Slipher's velocities, gave an age of about 2 billion years. That was wrong. Hubble's distances were wrong, off by a factor of 7, because he'd used the wrong calibration for Cepheids. But the method was sound. Measure distances, measure velocities, find the relationship, calculate the age. The equation that describes this relationship is dead simple. Velocity equals the Hubble constant times distance. That's it. If you know the distance to a galaxy and you know the Hubble constant, you can predict how fast it should be receding. If you know the velocity and the Hubble constant, you can calculate the distance. The Hubble constant is the proportionality factor linking the two. And the inverse of the Hubble constant, 1 divided by the Hubble constant, gives you what's called the Hubble time, an estimate of how long the universe has been expanding. That's not quite the same as the age of the universe, by the way. The Hubble time assumes the expansion rate has been constant, which it hasn't. Gravity has been slowing the expansion for most of cosmic history. Dark energy has been speeding it up for the last 5 billion years or so. The actual age depends on the details of how the expansion rate has changed over time. But the Hubble time gets you close. And in 1929, when Hubble published his paper, it was the first time anyone had a method for calculating the age of the universe that didn't rely on guesswork or theology. It came from measurements, observations, data. Here's what made Hubble's discovery so profound. The redshifts Slipher had measured weren't peculiar velocities. They weren't galaxies moving through space in random directions, like billiard balls bouncing around a table. They were recessional velocities caused by the expansion of space itself. Every galaxy, in every direction, was moving away from us. And the farther away a galaxy was, the more space there was between us and it, and the more that space had stretched, and the faster the galaxy appeared to be receding. This is one of the most misunderstood concepts in all of cosmology. People hear that galaxies are moving away from us, and they picture the Milky Way sitting at the center of the universe, with everything else flying outward. That's not what's happening. We are not at the center. There is no center. Space is expanding everywhere, uniformly, in all directions. If you were sitting in any other galaxy, you'd see the exact same thing. Every distant galaxy moving away from you, every nearby galaxy barely moving. The pattern is the same from every vantage point because the expansion is happening to space itself, not to objects moving through space. Imagine a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. Pick any raisin and call it home. From that raisin's perspective, all the other raisins are moving away. The farther away a raisin is, the faster it's receding, because there's more dough between them and all of that dough is expanding. But there's no center to the expansion. No special raisin that everything else is moving away from. The expansion is uniform. That's what's happening to the universe. We're one raisin. Every galaxy is a raisin. The dough is space, and the whole thing is expanding. Hubble didn't understand all of this in 1929. He reported the relationship between distance and velocity, but avoided speculating too much about what it meant. He was cautious. He knew his distances were uncertain. He knew the data were noisy. Other astronomers, including Lemaitre and Arthur Eddington, were quicker to embrace the idea of an expanding universe. Einstein, who'd spent years resisting the idea, finally accepted it after meeting Hubble and reviewing the data in the early 1930s. By the end of the decade, the expanding universe was the dominant model. The static universe was dead. But there was a problem. The Hubble constant Hubble calculated was way too large. His value implied the universe was expanding so fast that it could only be about 2 billion years old. Geologists by that time had solid evidence that Earth was at least 3 billion years old, possibly older. Rocks didn't lie. The numbers didn't work. Either the geologists were wrong, which seemed unlikely, or the Hubble constant was wrong, which seemed more likely but left cosmologists in an awkward position. The method was right. The result was absurd. The resolution took decades. Walter Baade figured out in the 1950s that there were two types of Cepheid variables with different luminosities, and Hubble had been using the wrong type. Once the correction was applied, the distances doubled. The Hubble constant dropped by half. The age of the universe increased to about 4 billion years. Still too young, but closer. Then in the 1970s and 80s, better telescopes and better distance measurements pushed the Hubble constant down further. The age estimate climbed to 10 billion years, then 12, then 13. By the early 2000s, data from the Wilkinson microwave anisotropy probe gave a Hubble constant of about 71 kilometers per second per megaparsec. The corresponding age was 13, 7 billion years, close enough to what we accept today that the basic picture was no longer in doubt. A megaparsec, by the way, is about 3.26 million light-years, so a Hubble constant of 71 means that for every 3.26 million light-years of distance, a galaxy's recessional velocity increases by 71 kilometers per second. A galaxy 10 megaparsecs away is receding at 710 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,100 kilometers per second. A galaxy a billion megaparsecs away, if such a thing were observable, would be receding faster than the speed of light. That sounds like it violates relativity. It doesn't. Relativity says nothing can move through space faster than light. It says nothing about space itself expanding. Space can stretch as fast as it wants, and at large enough distances, it does. There's a horizon out there, a distance beyond which galaxies are receding so fast that their light will never reach us. Not because the light isn't traveling, it is. It's moving toward us at the speed of light. But the space between us and those galaxies is expanding faster than light can cross it. The light makes progress, but the finish line is moving away faster than the light is moving forward. We will never see those galaxies. They are beyond the edge of the observable universe, not because they don't exist, but because the expansion of space has put them permanently out of reach. That's a direct consequence of Hubble's law. If velocity increases with distance and space is expanding uniformly, then at some distance the recessional velocity exceeds the speed of light. Beyond that point, no information can reach us. The observable universe has a boundary, not because space ends, but because we've run out of time. Light from galaxies beyond that boundary hasn't had enough time to reach us yet, and if the expansion keeps accelerating, it never will. Hubble's law only works at large scales. It breaks down locally. Andromeda is moving toward us, not away. That's because Andromeda is close enough that its motion is dominated by gravity, not expansion. The Milky Way and Andromeda are gravitationally bound. They're falling toward each other. In a few billion years, they'll collide and merge. The expansion of space is still happening between us and Andromeda, but the rate is so slow over that short distance that gravity overwhelms it. Galaxies in the same cluster or the same group don't obey Hubble's law. They have what astronomers call peculiar velocities, their own individual motions through space caused by gravitational interactions with their neighbors. It's only when you look at galaxies far enough away, tens of millions of light-years or more, that Hubble's law dominates and the expansion of space becomes the primary driver of recessional velocity. That means redshift has two components. One is cosmological redshift, caused by the stretching of space itself as light travels across billions of light years. The other is Doppler redshift, caused by the galaxy's motion through space relative to its local environment. For nearby galaxies, the Doppler component can be significant. For distant galaxies, cosmological redshift dominates. Measuring both and separating them requires careful analysis. Here's where the Hubble constant becomes critical for calculating the age of the universe. If you know how fast the universe is expanding today, and you know how the expansion rate has changed over time, you can run the clock backward and figure out when everything was in the same place. That moment, when the distance between all points in space was zero, is the Big Bang. The time between then and now is the age of the universe. The Hubble constant is the key input. Get it wrong, and your age estimate is wrong. Get it right, and the timeline snaps into focus. The problem, and this is where things get uncomfortable, is that the Hubble constant is not as well pinned down as you'd hope. Measurements made using the cosmic microwave background give one value. Measurements made using Cepheids and supernovae give another. The two methods don't agree. They're close, within about 10% of each other, but they don't overlap within their stated uncertainties. That gap is called the Hubble tension, and it's been growing more obvious as measurements get more precise. The cosmic microwave background, analyzed by the Planck satellite, gives a Hubble constant of about 67 kilometers per second per megaparsec. The distance ladder, refined by Adam Rees and his team using the Hubble Space Telescope and now the James Webb Space Telescope, gives a value closer to 73. That's not a small disagreement. A Hubble constant of 67 implies the universe is about 13.8 billion years old. A Hubble constant of 73 implies it's about 12.8 billion years old. That's a difference of a billion years. For a while, people thought the tension would go away with better data. It hasn't. If anything, it's gotten worse. Both sides have refined their measurements. Both sides are confident in their methods, and the numbers refuse to converge. Some astronomers think there's a systematic error somewhere. Maybe the Cepheid calibrations are off. Maybe dust is affecting the supernova measurements in ways we haven't accounted for. Maybe the cosmic microwave background analysis relies on assumptions about dark matter or dark energy that aren't quite right. Others think the tension is real and that the standard model of cosmology is missing something. Maybe dark energy behaves differently than we thought. Maybe the expansion rate has changed in unexpected ways. Maybe there's new physics hiding in the gap. For now, the tension sits there, unresolved, a reminder that even when you think you've nailed down a number as fundamental as the age of the universe has a way of keeping you humble. Hubble's law works. The expanding universe is not in doubt. Redshift is real. The relationship between distance and velocity is observed, measured, and confirmed across billions of light years. But the exact value of the Hubble constant, the number that sets the scale for everything, is still a matter of active debate, and that debate is where we're going next. We've established that galaxies are moving away from us, that the farther away they are, the faster they're receding, and that this relationship, Hubble's law, gives us a way to calculate how long the universe has been expanding. Measure the rate of expansion today, run the clock backward, and you get the age of the universe. Simple, clean, elegant, except for one problem. The rate of expansion today, the Hubble constant, is not a number everyone agrees on, and the disagreement is not small. It's not a rounding error. It's a gap large enough that depending on which measurement you trust, the universe could be nearly a billion years older or younger than the textbooks say. This is the Hubble tension. And it's one of the most uncomfortable problems in modern cosmology because both sides have good data. Both sides have done the work. Both sides are using methods that have been tested and refined for decades, and the numbers refuse to meet in the middle. The more precise the measurements get, the more obvious the problem becomes. This isn't a case where one group made a mistake and the other caught it. This is a case where two independent approaches to measuring the same thing are giving different answers, and nobody knows why. Let's start with what the Hubble constant actually is, because the name is misleading. It's called a constant, but it's not constant over time. The expansion rate of the universe has been changing since the Big Bang. It was faster in the early universe. It slowed down as gravity pulled on everything. Then, about 5 billion years ago, it started speeding up again as dark energy took over. The Hubble constant is the expansion rate right now, today, at this moment in cosmic history. It's a snapshot, not a fixed value. And because the universe has been evolving, the Hubble constant you measure depends on when and how you measure it. The number itself has units that sound awkward if you're not used to them. Kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So if the Hubble constant is, say, 70 kilometers per second per megaparsec, that means for every 3.26 million light-years of distance, a galaxy's recessional velocity increases by 70 kilometers per second. A galaxy 10 megaparsecs away is receding at 700 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,000 kilometers per second. The relationship is linear. Distance times the Hubble constant equals velocity. That's the rule. Edwin Hubble's original estimate in 1929 was about 500 kilometers per second per megaparsec, absurdly high. That number implied the universe was only about 2 billion years old, younger than Earth, which was a problem. The issue was that Hubble's distances were wrong. He'd used Cepheid variables to measure distances to nearby galaxies, but he'd used the wrong calibration. Walter Baade figured out in the 1950s that there were two types of Cepheids with different luminosities, and Hubble had been mixing them up. Once the correction was applied, the distances doubled. The Hubble constant dropped to around 250. Still too high, but closer. Over the following decades, better telescopes and better distance measurements pushed the number down further. By the 1970s, estimates ranged from about 50 to 100, a huge spread. Cosmology at that point was still a messy field. The spread started narrowing in the 1990s. Two things happened. First, the Hubble Space Telescope launched in 1990 and gave astronomers the ability to observe Cepheids in galaxies much farther away than ground-based telescopes could reach. Second, astronomers developed better techniques for measuring distances using Type I supernovae, which are bright enough to be seen across billions of light-years. In 1994, a team led by Wendy Friedman launched the Hubble Key Project, a multi-year effort to measure the Hubble constant with unprecedented precision. They observed Cepheids in 31 galaxies, calibrated their distances, and used those distances to refine the brightness of Type I supernovae. Their final result, published in 2001, was 72 kilometers per second per megaparsec, with an uncertainty of about 8. That was a landmark. For the first time, the Hubble constant had been pinned down to within roughly 10%. At the same time, a separate team led by Adam Rees was using Type I supernovae to study the expansion history of the universe. They weren't trying to measure the Hubble constant directly. They were trying to figure out whether the expansion was slowing down. The answer, published in 1998, was no. The expansion was speeding up. That discovery, which earned Rees and his colleagues the Nobel Prize in 2011, forced cosmologists to add dark energy to their models. And once dark energy was included, the age of the universe changed. The expansion history was more complicated than anyone had assumed. The Hubble constant wasn't just a number, it was a window into the entire evolution of the cosmos. Rees kept refining his measurements. He formed a collaboration called SH0ES, which stands for supernova H0 for the equation of state. The goal was to measure the Hubble constant using the most reliable distance indicators available, Cepheids for nearby galaxies, Type 1, a supernovae for more distant ones. The method is straightforward. Find a galaxy where you can see individual Cepheid variable stars, measure their periods, calculate their distances, then wait for a Type 1, a supernova, to explode in that same galaxy. Measure the supernova's peak brightness. Now you know how bright a Type 1, a supernova looks at a known distance. Use that calibration to measure distances to other galaxies where supernovae have exploded, but Cepheids are too faint to see. Repeat hundreds of times. Refine the error bars. Tighten the uncertainties. By 2016, the SH0ES team had measured the Hubble constant to a precision of about 4.5%. Their value was 73.24 kilometers per second per megaparsec, with an uncertainty of 1.74. That was the most precise direct measurement anyone had ever made, and it didn't match what the cosmic microwave background was saying. The cosmic microwave background gives you a completely different way to measure the Hubble constant. You're not looking at nearby galaxies, you're not measuring distances to stars. You're analyzing the faint glow of radiation left over from when the universe was 380,000 years old. That radiation has tiny temperature fluctuations across the sky, ripples imprinted during the early universe when sound waves were bouncing through the hot plasma before atoms had formed. The size and shape of those ripples encode information about the universe's composition, geometry, and expansion rate. By measuring the ripples precisely and plugging them into the standard model of cosmology, you can calculate what the Hubble constant should be today. The European Space Agency's Planck satellite spent 4.5 years mapping the cosmic microwave background with exquisite precision. The final results, released in 2018, gave a Hubble constant of 67.4 kilometers per second per megaparsec, with an uncertainty of about half a kilometer per second per megaparsec. That's incredibly precise. The error bars are tight, and the number is 6 kilometers per second per megaparsec lower than what the SH0ES team measured. 6 doesn't sound like a lot, but when your uncertainties are less than 2, a gap of 6 is enormous. Statistically, it's a 3 sigma discrepancy. The probability that the difference is due to random chance is less than 1 in 1,000. So what's going on? There are 3 possibilities, and none of them are comfortable. The first is that one of the measurements is wrong. Maybe there's a systematic error in the Cepheid calibrations. Maybe dust is dimming distant supernovae in ways the models don't account for. Maybe the analysis of the cosmic microwave background relies on assumptions that don't hold. Both teams have been checking and rechecking their work for years. Both have refined their methods. Both have reduced their uncertainties, and the gap hasn't closed. If anything, it's gotten wider. The second possibility is that the standard model of cosmology, the framework that's been guiding the field for decades, is incomplete. Maybe dark energy behaves differently than the models assume. Maybe the expansion rate has changed in ways we haven't accounted for. Maybe there's new physics hiding in the gap between the early universe and today. That's exciting if you're a theorist. It's also deeply unsettling because the standard model works extraordinarily well for almost everything else. The abundances of hydrogen and helium, The formation of structure, the distribution of galaxies, all of it fits. Changing the model to fix the Hubble tension without breaking everything else that works is hard. The third possibility is that both measurements are right and the universe is more complicated than we thought. Maybe the Hubble constant isn't the same everywhere. Maybe the expansion rate varies from region to region. That would violate one of the core assumptions of cosmology, which is that the universe is roughly the same in all directions on large scales, but it's not impossible. If we happen to live in a region where the local density is slightly different from the cosmic average, that could bias our measurements. That idea has problems of its own. The cosmic microwave background looks incredibly uniform. If the universe varied significantly from place to place, we'd expect to see evidence of that in the background radiation. We don't. Here's where things get uncomfortable. In 2025, a combined analysis of data from the Planck satellite, the South Pole Telescope, and the Atacama Cosmology Telescope gave a Hubble constant of 67.24 kilometers per second per megaparsec. Tighter error bars, same basic number. Meanwhile, the SH0ES team has continued refining their measurements using the James Webb Space Telescope, which can resolve Cepheids in galaxies where Hubble's images were too crowded and blurry. Webb's sharper vision was supposed to resolve the tension. It hasn't. If anything, Webb's data have confirmed the local measurements. The Hubble constant, measured using the distance ladder, is 73.5, give or take 1. The Hubble constant, measured using the cosmic microwave background, is 67.4, give or take half. The gap is real, it's persistent, and it's not going away. Other methods have been tried. Gravitational lensing, where the light from a distant quasar is bent around a foreground galaxy, can be used to measure distances and expansion rates independently of Cepheids and supernovae. A collaboration called H0 LICO, which stands for H0 lenses in Cosmograil's wellspring, used this technique and got a value of about 73.3 kilometers per second per megaparsec, close to what SH0ES found. Then there's the standard siren method, which uses gravitational waves from merging neutron stars. When two neutron stars collide, they emit gravitational waves that can be detected by observatories like LIGO and Virgo. If the collision also produces light, you can measure the distance using the gravitational wave signal and the redshift using the light. That gives you an independent measurement of the Hubble constant. The first measurement, from an event detected in 2017, gave a value around 70 kilometers per second per megaparsec. The uncertainties were large, but the number fell closer to the local measurements than the cosmic microwave background value. What's frustrating is that every direct measurement, every method that looks at objects in the relatively nearby universe, gives a Hubble constant around 73. Every indirect measurement, every method that extrapolates from the early universe forward using the standard model, gives a number around 67. The split is clean: local universe, high; early universe, low. That pattern suggests the problem isn't with the measurements themselves. The problem is with the model connecting them. The implications are profound. If the Hubble constant is 73, the universe is expanding faster today than the standard model predicts. That means either dark energy is stronger than we thought, or it's behaving differently, or there's something else accelerating the expansion that we haven't identified. Some theorists have proposed early dark energy, a burst of accelerated expansion in the first few 100,000 years after the Big Bang, that would have nudged the conditions in the early universe just enough to shift the prediction from 67 to 73. That idea is speculative. It requires adding new physics to the standard model. And while it solves the Hubble tension, It doesn't solve anything else, which makes it feel like a band-aid rather than a cure. Others have suggested modifications to gravity. Maybe Einstein's general relativity is almost right, but breaks down slightly on the largest scales. Maybe the expansion rate isn't the same in all directions. Maybe dark matter interacts with regular matter more strongly than we've assumed, altering the way structure forms and changing the predicted expansion rate. All of these ideas are on the table. None of them have enough evidence to be taken seriously yet. But the fact that physicists are even discussing them tells you how uncomfortable the Hubble tension has become. Here's the thing. The Hubble constant doesn't just set the expansion rate, it sets the age of the universe. If the Hubble constant is 67, the universe is about 13.8 billion years old. If it's 73, the universe is about 12.8 billion years old. That's a difference of 1 billion years. For most purposes, that difference doesn't matter. The oldest stars are still younger than the universe. Galaxies still had time to form. Life still had time to evolve. But for cosmologists trying to build a precise timeline of cosmic history, 1 billion years is huge. It changes when the first stars ignited. It changes when galaxies began merging. It changes the entire narrative. And it's not just the age. The Hubble constant feeds into calculations of dark energy density, dark matter abundance, the curvature of space, the rate at which structure formed. Change the Hubble constant, and you change all of those. If 73 is the right number, then the Standard Model's predictions for the early universe are off. If 67 is right, then something about the way we're measuring distances in the local universe is biased. Either way, something is wrong, and figuring out what is going to require better data, better models, or both. Wendy Friedman, who led the Hubble Key project and has been measuring the Hubble constant for more than 3 decades, has taken a different approach. She's been using alternative distance indicators that don't rely as heavily on Cepheids. Red giant stars, for instance, have a predictable maximum brightness called the tip of the red giant branch. You can use that as a distance marker. Another method involves a type of star called a J-branch star, which also has predictable brightness. Friedman's team has been using the James Webb Space Telescope to measure distances with these methods. In August 2024, they published results from 3 different techniques. The red giant method gave a Hubble constant around 68. The J-branch method gave around 70. The Cepheid method gave 72. The spread within her own measurements was almost as large as the spread between the local and early universe values. That complicates things. It suggests the distance ladder itself might have unresolved issues that no single telescope can fix. Adam Rees responded by arguing that Friedman's team had used a small sample of supernovae and that the selection could have biased the results. The debate has become one of the most closely watched in modern astrophysics. Both sides are careful, both are rigorous, both are pointing at real data, and the numbers still don't agree. There's one more wrinkle. The Hubble constant measured using the cosmic microwave background assumes the Standard Model is correct. It assumes dark matter behaves the way we think it does. It assumes dark energy is constant over time. It assumes the universe is flat and homogeneous on large scales. Those are good assumptions. They're supported by decades of observations, but they're still assumptions. If any of them are slightly wrong, the predicted Hubble constant changes. The SH0 measurement, on the other hand, doesn't assume anything about dark energy or dark matter. It's empirical. It's based on direct observations of stars and explosions. That makes it harder to dismiss. So where does that leave us? As of 2025, the Hubble tension is still a mystery. No consensus exists. Both sides have published papers arguing their methods are sound. Both have reduced their uncertainties to the point where the discrepancy can't be explained by measurement error. The simplest explanation, that someone made a mistake, looks increasingly unlikely. The more interesting explanation, that the universe is trying to tell us something and we're not listening carefully enough, is gaining traction. This is how science works when it's working right. You gather data, you refine your methods, you tighten your error bars, and if the numbers refuse to converge, you admit you don't understand something. You don't fudge the data to make it fit. You don't ignore the measurements you don't like. You sit with the discomfort and you keep looking. The Hubble tension is uncomfortable. It's also exciting. Because the last time cosmology had a major discrepancy like this, when observations didn't match predictions, it led to the discovery of dark energy, a completely unexpected component of the universe that makes up 70% of its total energy density. The Hubble tension might be pointing at something equally profound, or it might just be dust, or calibration errors, or bad luck in how the data lined up. We won't know until more measurements come in. Future telescopes, better distance indicators, independent checks using gravitational waves and gravitational lensing, all of that will help. But for now, the Hubble constant is a number with two answers. And depending on which answer you trust, the universe is either 13.8 billion years old or 1 billion years younger. That's not a small problem. That's a crisis, and it's sitting right at the center of modern cosmology, refusing to resolve itself. The good news is that cosmologists aren't giving up. They're building better instruments, they're refining the models, they're checking every assumption. And sooner or later, the tension will either disappear or it will crack the standard model wide open. Either outcome is interesting. Either outcome moves the field forward, because the universe doesn't care what we think. It is what it is. And if our models don't match what the universe is doing, the models have to change. That's the rule. That's always been the rule. And the Hubble tension is the universe's way of reminding us that we're not done yet. But the Hubble constant isn't the only way to measure cosmic time. There are other clocks ticking in the universe. Older clocks. Stars so ancient they were born when the cosmos was still in its infancy. Elements forged in the first few minutes after the Big Bang. Independent lines of evidence that don't rely on expansion rates or distance ladders or assumptions about dark energy. And if you want to know whether 13.8 billion years is the right answer, you need to check those clocks too. That's where we're going next. We've spent time now walking through the measurements that rely on expansion, on redshift, on light stretched across billions of years of cosmic growth. The cosmic microwave background gives one number, the distance ladder gives another. Both methods depend on models, on assumptions about how space has been stretching since the beginning. And right now, those two methods don't quite agree. The Hubble tension sits there, unresolved, a gap of about 6 kilometers per second per megaparsec between what the early universe predicts and what nearby galaxies show. That's uncomfortable. It suggests either the measurements are off or the models are incomplete. So before anyone accepts 13.8 billion years as the final word, you want a second opinion. Actually, you want several. You want methods that don't depend on expansion rates or cosmological models or assumptions about dark energy. You want objects you can point at and date directly. Objects that have been sitting in space, aging quietly since the universe was young. Objects whose ages give you a minimum boundary, a floor beneath which the universe cannot possibly be younger. You want the oldest stars. Stars are not eternal. They're born, they live, they die, and the way they age is predictable. A star's life is a battle between gravity, which wants to crush it, and nuclear fusion, which pushes outward. For most of a star's life, those forces balance. Hydrogen fuses into helium in the core. The energy released keeps the star inflated, but eventually the hydrogen runs out. What happens next depends on the star's mass. Massive stars burn through their fuel quickly, fuse heavier and heavier elements, and explode as supernovae within a few million years. Smaller stars, stars with masses similar to our Sun or less, take their time. They burn hydrogen for billions of years. Some of them, the smallest ones, have lifetimes longer than the current age of the universe. They're still on their first tank of fuel. They haven't had time to evolve yet. That's useful, because if you can find a star that's just now running out of hydrogen, just now starting to evolve off what astronomers call the main sequence, you know that star has been burning for as long as it takes to exhaust its core hydrogen supply. For a Sun-like star, that's about 10 billion years. For a star slightly less massive, it could be 12 billion years, 13 billion, 14. The smaller the star, the longer it takes. And if you find a cluster of stars, all born at the same time, you can look at which stars have started to evolve and which haven't. The point where stars are just beginning to leave the main sequence tells you the age of the cluster. It's called the main sequence turnoff, and it's one of the most reliable cosmic clocks we have. Globular clusters are perfect for this. They're dense, spherical collections of stars, typically containing hundreds of thousands to millions of stars packed into a region only a few dozen light-years across. They orbit galaxies in halos, far above and below the galactic disk, and they're old, extraordinarily old. The stars in globular clusters are metal-poor, meaning they contain very little of anything heavier than hydrogen and helium. That's a signature of early formation. The first generations of stars in the universe had almost no metals because the Big Bang only produced hydrogen, helium, and trace amounts of lithium. Everything heavier was made later, inside stars. So when you find stars with very low metal content, you know they formed early, before the universe had time to pollute itself with the ashes of dead stars. Our galaxy, the Milky Way, has about 150 known globular clusters. Some of them are absurdly ancient. The cluster known as M92, located about 27,000 light-years from Earth, has been studied extensively. For a long time, estimates of its age were rough, somewhere between 12 and 15 billion years. The uncertainty was large because dating stars is hard. You need precise measurements of their brightness, their color, their temperature. You need to know the distance to the cluster accurately. You need to account for dust between us and the stars, which dims and reddens the light. You need stellar evolution models that correctly predict how stars of different masses change over time. Any error in those inputs propagates into the final age estimate. In recent years, better telescopes and better techniques have tightened those estimates. A refined analysis of M92, published in the 2020s, gave an age of 13.8 billion years, plus or minus 0.75 billion. That's tight. The uncertainty is less than 6%, and the central value matches almost exactly the age of the universe derived from the cosmic microwave background. That's not a coincidence engineered to make the numbers fit. That's an independent measurement using stellar physics, and it's telling you the same story the microwave background told. The universe is about 13.8 billion years old, and M92 formed very close to the beginning. The technique used to date M92 and other globular clusters is called isochrone fitting. An isochrone is a theoretical curve that shows where stars of different masses sit on a plot of brightness versus temperature at a specific age. You take your stellar evolution models, plug in an age, say 12 billion years, and calculate where stars of various masses should appear on that plot. Then you plot the actual stars in the cluster and see if they match. If they don't, you adjust the age and try again. When the theoretical curve lines up with the real data, you've found the cluster's age. The main sequence turnoff is the key feature. It's the point where stars have just exhausted their core hydrogen and are starting to evolve into red giants. That turnoff moves to fainter, cooler stars as the cluster gets older because lower mass stars take longer to burn through their hydrogen. The method works because stellar evolution is well understood. Stars are not mysterious. They're balls of gas held together by gravity, powered by nuclear fusion. The physics is clean. The equations are solvable. Given a star's mass and composition, you can predict its luminosity, temperature, and lifetime with high precision. Uncertainties exist, sure. Rotation can affect a star's evolution. Magnetic fields can play a role. Binary stars can exchange mass, complicating the picture. But for most stars in a globular cluster, those effects are small. The main drivers, gravity and fusion, are dominant. And the predictions match observations well enough that isochrone fitting has become one of the most trusted methods for dating old stellar populations. The oldest globular clusters in the Milky Way have ages clustering around 13 billion years. Multiple studies using different methods, different telescopes, different assumptions, all converge on that number. Some estimates go as high as 13.5 billion years, some go as low as 12 billion, but the range is tight, and the average is about 13 billion, give or take a billion. That gives you a lower limit on the age of the universe. The universe cannot be younger than its oldest stars. If the oldest stars are 13 billion years old, the universe has to be at least that old, probably older, because those stars didn't form the instant the Big Bang happened. There was a delay. The universe had to cool, atoms had to form, gas clouds had to collapse. The first stars didn't ignite until somewhere between 100 million and a few hundred million years after the Big Bang. So if the oldest stars are 13 billion years old and they formed a few hundred million years in, the universe itself is probably closer to 13.5 or 13.8 billion years old, which, again, matches what the cosmic microwave background says. Some globular clusters might have formed even earlier. There's evidence that a handful of the Milky Way's globular clusters, particularly the most metal-poor ones, could have formed less than 300,000 years after the Big Bang. That's shockingly early. 300,000 years is roughly the age of the universe at recombination, the moment the cosmic microwave background was released. If clusters were already forming by then, it suggests structure in the universe assembled faster than many models predict. That's consistent with some of the tensions cosmologists are seeing with the James Webb Space Telescope, which has been finding galaxies at high redshifts that look more mature than expected. The early universe was busier than we thought. Absolute age estimates for Milky Way globular clusters typically fall between 11.5 and 13.5 billion years, with uncertainties of about 500 million to 750 million years. That's the range supported by multiple independent analyses. The spread reflects real differences between clusters, some formed earlier than others. The Milky Way assembled over time, accreting smaller galaxies and their globular clusters. The oldest clusters probably formed before the Milky Way itself existed, in smaller proto-galaxies that later merged. The younger ones formed later, after the galaxy had already taken shape. But even the youngest globular clusters are old by human standards. 11 billion years is a long time. And the fact that the oldest ones push right up against the age of the universe tells you that star formation started early and continued. There's another class of stars that serve as cosmic clocks, and they're less famous but equally important: subdwarfs. These are old, metal-poor stars that have left the main sequence and are evolving toward the white dwarf stage. They're hotter and bluer than red giants, but dimmer than main sequence stars of the same temperature. They sit in a specific region of the brightness-temperature diagram, and their properties are stable and predictable. Because their evolution is slow and their physics is well understood, subdwarfs can be used to refine age estimates for stellar populations. They're particularly useful for clusters where the main sequence turn-off is hard to measure precisely, either because the cluster is distant or because dust obscures the faintest stars. Subdwarfs are brighter than turn-off stars, easier to observe, and they carry the same age information. The ages derived from globular clusters don't depend on cosmological models. They don't depend on the Hubble constant. They don't depend on assumptions about dark energy or the curvature of space. They depend on stellar physics. And stellar physics, while not perfect, is one of the most well-tested areas of astrophysics. We've observed stars at every stage of their lives. We've seen them born in nebulae. We've watched them evolve on human timescales in some cases, particularly for very massive stars that live only a few million years. We've seen them die as supernovae, as planetary nebulae, as white dwarfs. The models work. They predict observations. And when those models tell you a star is 13 billion years old, that's a number you can trust. But stars aren't the only independent clock. There's another method, one that doesn't look at objects in space, but at the composition of space itself. The abundances of the lightest elements in the universe. Hydrogen, helium, lithium. Those three elements were forged in the first few minutes after the Big Bang, during a process called Big Bang nucleosynthesis. And the ratios in which they were produced depend on the conditions in the early universe, the temperature, the density, the expansion rate. By measuring those abundances today and comparing them to theoretical predictions, you can constrain the age and properties of the universe in a way that's completely independent of distance measurements or stellar evolution. Here's how it works. In the first second after the Big Bang, the universe was too hot for atomic nuclei to exist. Protons and neutrons were floating freely in a sea of radiation, constantly being created and destroyed by high-energy photons. As the universe expanded and cooled, a threshold was crossed. Around 1 second after the Big Bang, the temperature dropped below about 10 billion Kelvin. At that point, protons and neutrons stopped interconverting. The ratio of protons to neutrons froze in at about 7:1. Protons outnumbered neutrons because neutrons are slightly heavier and less stable. Free neutrons decay into protons with a half-life of about 10 minutes. But if a neutron gets bound into a nucleus before it decays, it becomes stable. Between about 1 second and 3 minutes after the Big Bang, the universe was still hot enough for nuclear fusion to occur. Protons and neutrons started sticking together, forming the lightest atomic nuclei. 2 protons and 2 neutrons fused into helium-4. Some deuterium formed, a heavy isotope of hydrogen with 1 proton and 1 neutron. Trace amounts of helium-3 and lithium-7 were produced. The process stopped after about 3 minutes, because by then the universe had expanded and cooled enough that fusion could no longer occur. The nuclei that had formed were locked in. No more would be made until the first stars ignited hundreds of millions of years later. The final abundances depend on the conditions during those first 3 minutes. If the universe was denser, fusion happened more efficiently and more helium was produced. If it was less dense, less helium formed. If the expansion was faster, there was less time for fusion and the abundances changed. If the ratio of protons to neutrons was different, the final mix shifted. The physics is well understood. The nuclear reaction rates are known. You can plug in the conditions and predict exactly how much hydrogen, helium, and lithium should have been produced. The predictions are precise. So what do we observe? About 75% of the universe's ordinary matter, by mass, is hydrogen. About 25% is helium. Everything else, all the heavier elements, carbon, oxygen, iron, gold, makes up less than 2%. And almost all of that 2% was made in stars. The hydrogen and helium are primordial. They're leftovers from the Big Bang. When you measure the helium abundance in old, metal-poor stars and gas clouds, stars that haven't been polluted much by stellar nuclear synthesis, you find about 25% helium by mass. That matches the prediction from Big Bang nuclear synthesis almost exactly. Lithium is trickier. The predicted abundance is higher than what's observed in old stars. That discrepancy, called the lithium problem, has been bothering cosmologists for decades. Possible explanations include lithium being destroyed in stellar interiors or being depleted in the early universe by processes we don't fully understand. But the lithium problem doesn't break the overall picture. Hydrogen and helium match beautifully, and the deuterium abundance, which is harder to measure but has been detected in distant gas clouds, also matches predictions. The key point is that the abundances of these light elements constrain the conditions in the early universe. And those conditions, the density, the temperature, the expansion rate, are directly tied to the age of the universe. If the universe were significantly younger than 13.8 billion years, the expansion rate would have been different during Big Bang nucleosynthesis. That would change the predicted helium abundance. The fact that the observed abundance matches the prediction so closely tells you the models are right. The universe is the age we think it is. The expansion history we've calculated is correct. This is an independent check that doesn't rely on measuring distances to galaxies or fitting stellar evolution models to globular clusters. It relies on nuclear physics and the composition of the cosmos. There's one more method worth mentioning, though it's less precise: radioactive dating. Certain isotopes, like uranium-238 and thorium-232, decay slowly over billions of years. By measuring the abundances of these isotopes in old stars and comparing them to theoretical predictions of how much should have been produced in supernova explosions, you can estimate how long it's been since those elements were created. This technique has been applied to stars in the Milky Way's disk, particularly old stars with low metal content. The ages derived from radioactive isotopes typically come in around 10 billion years, give or take a few billion. The uncertainties are large because the method depends on assumptions about how and when these elements were produced, which in turn depends on the history of star formation and supernova rates in the galaxy. It's model-dependent in ways that stellar ages and primordial abundances are not. But it provides another data point, another line of evidence pointing in the same direction. What's remarkable is that all of these methods, different techniques using different physics applied to different objects, converge on the same answer. The oldest globular clusters are about 13 billion years old. The abundances of hydrogen and helium match predictions for a universe that's 13.8 billion years old. The cosmic microwave background says 13.8 billion years. The distance ladder, depending on whose measurements you trust, says somewhere between 12.8 and 13.8 billion years. The spread is there, yes. The Hubble tension is real, but the range is narrow. Nobody's getting 5 billion years or 20 billion years. Everyone's getting something close to 13 or 14 billion. That convergence is what gives cosmologists confidence. If one method gave a wildly different answer, you'd know something was broken. The fact that they all agree within the uncertainties tells you the basic picture is right. It's worth pausing to appreciate how extraordinary this is. A century ago, nobody knew how old the universe was. 50 years ago, estimates ranged from 10 billion to 20 billion years. Today, multiple independent methods using completely different physics all point to an age of about 13.8 billion years, with uncertainties of less than a billion years. Some methods are more precise than others. Some rely on models that might need refining. But the agreement is striking. You're not just trusting one measurement. You're trusting a web of cross-checks, each method validating the others. The oldest stars give you a flaw. The universe cannot be younger than 13 billion years because stars that old exist. Big Bang nucleosynthesis gives you a constraint on the conditions in the early universe, and those conditions are consistent with an age of 13.8 billion years. The cosmic microwave background gives you a snapshot of the universe at 380,000 years old, and the physics connecting that snapshot to today predicts an age of 13.8 billion years. The expansion rate measured using supernovae, if you take the cosmic microwave background's value, also points to 13.8 billion years. Every method has uncertainties, every method has assumptions, but they all point the same direction. And when that happens in science, when independent lines of evidence converge, you start to believe the answer is real. There are still puzzles. The Hubble tension hasn't gone away. The lithium problem is unsolved. Some of the galaxies the James Webb Space Telescope has found at high redshifts look more massive and more mature than models predict, suggesting the early universe was more active than expected. Those puzzles don't invalidate the age measurement, they complicate it. They suggest the story is more nuanced than the standard model allows. But they don't change the fact that the universe is roughly 13.8 billion years old. That number is robust. It's survived decades of scrutiny. It's been refined, tested, cross-checked, and it's held up. Stars are clocks. Elements are clocks. Expansion is a clock. And all of those clocks, when read carefully, tell the same time. 13.8 billion years since the beginning. That's the timeline. That's the age of everything. And now that we've established how we know that number, how we've measured it from multiple angles using different methods and different objects scattered across the cosmos, we can finally walk through what actually happened during those 13.8 billion years, the full history, the cosmic timeline. From the first fraction of a second after the Big Bang to the moment you started reading this. That's where we're going next. The story of how an incomprehensibly hot, dense, uniform state became a universe filled with galaxies, stars, planets, and at least one species capable of looking back and figuring out how long it's all been running. We've walked through the methods, the cosmic microwave background mapping the early universe at 380,000 years old, the distance ladder climbing from nearby Cepheids to distant supernovae, the oldest stars setting a floor at 13 billion years, the primordial abundances of hydrogen and helium locked in during the first few minutes, every independent technique pointing at the same number. 13.8 billion years, give or take 37 million, which on cosmic scales is nothing. That's the age of the universe. That's how long this has all been running. And now that we've established the number and shown how we measured it, we can finally do what humans have been trying to do since the first time someone looked up and wondered where it all came from. We can tell the story, the full story, beginning to now. 13.8 billion years of cosmic history compressed into something a human brain can hold. This is that timeline. The universe does not start gently. There is no slow build-up, no gradual warming, no moment where conditions ease into existence. At time zero, everything that would ever exist, all the matter, all the energy, all the space, all the time, is compressed into a region smaller than the period at the end of this sentence, smaller than an atom, smaller than a proton. A singularity of infinite density and infinite temperature, where every known law of physics collapses into mathematical nonsense. General relativity breaks, quantum mechanics breaks. We have equations that describe what happens 1 second after the beginning. We have no equations that describe the beginning itself. That era, the first 10 to the negative 43 seconds, is called the Planck epoch, named after Max Planck, whose work on quantum mechanics inadvertently set the scale where space-time itself becomes grainy and uncertain. We don't know what happened during the Planck epoch. We can't know. Our physics doesn't reach that far. But whatever happened, it ended, and what came next changed everything. Somewhere between 10 to the negative 36 and 10 to the negative 32 seconds after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. This was not the steady Hubble expansion we see today. This was violent. Space itself stretched faster than light, doubling in size every fraction of a second. In less time than it takes light to cross a proton, a region smaller than an atom inflated to the size of a grapefruit, then a basketball, then larger than the solar system. The entire observable universe today, everything we can see in any direction, every galaxy, every star, every photon of the cosmic microwave background, all of it came from a patch of space smaller than the tip of a needle. Inflation smoothed out the universe. It stretched away any large-scale irregularities, any wrinkles in space-time, leaving behind a cosmos that was astonishingly uniform, almost perfectly smooth. The tiny quantum fluctuations that existed before inflation got stretched too, blown up from subatomic scales to cosmic scales. Those stretched fluctuations became the seeds of structure, the slight variations in density that would eventually collapse under gravity to form galaxies. Without inflation, the universe would look nothing like it does today. We needed that burst. That moment of cosmic violence in the first billionth of a trillionth of a second. Without it, we wouldn't be here. When inflation ended, the energy driving it decayed into particles, matter, radiation. The universe was suddenly filled with a hot, dense soup of fundamental particles. Quarks, gluons, electrons, neutrinos, photons. Everything smashing into everything else at energies so high that nothing stable could form. This era is called the quark-gluon plasma phase, and it lasted for about 1/1,000,000th of a second. The temperature at this point was around 10,000 trillion degrees Kelvin. Hot enough that protons and neutrons couldn't exist. Quarks, the building blocks of protons and neutrons, were flying free, constantly colliding, constantly being created and destroyed by the ambient radiation. There were no atoms, no nuclei, just a chaotic sea of particles and energy filling all of space. Then the universe cooled. Not because anything was absorbing the heat, because space was expanding. Expansion cools things down. Stretch a hot gas, and it gets cooler. Stretch space-time itself, and everything in it cools. By the time the universe was about 1 microsecond old, the temperature had dropped below 1,000,000,000,000 degrees. That's still absurdly hot, but it was cool enough for quarks to start binding together. Protons formed, neutrons formed. These are the particles that make up atomic nuclei. Once they appeared, they were stable. The universe had crossed a threshold. It now contained the raw ingredients for matter as we know it. But protons and neutrons weren't bonding together yet. The universe was still too hot. Free neutrons are unstable. Left alone, a neutron decays into a proton, an electron, and a neutrino with a half-life of about 10 minutes. So neutrons were decaying. The ratio of protons to neutrons, which started at about 50-50 when quarks first bound together, began shifting toward more protons. By the time the universe was about 1 second old, the ratio had frozen at about 7 protons for every neutron, and the temperature had dropped to around 10 billion degrees Kelvin. For reference, that's about 600 times hotter than the core of the Sun. Still unimaginably hot, but cool enough for the next phase to begin. Between about 1 second and 3 minutes after the Big Bang, nuclear fusion occurred throughout the entire universe. This period is called Big Bang nucleosynthesis, and it's one of the most important events in cosmic history. Protons and neutrons started sticking together, fusing into the lightest atomic nuclei. Most of the neutrons got locked into helium-4, a stable nucleus with 2 protons and 2 neutrons. Some deuterium formed, heavy hydrogen with 1 proton and 1 neutron. Trace amounts of helium-3 and lithium-7 were produced. The process lasted about 3 minutes. After that, the universe had expanded and cooled enough that fusion stopped. The nuclei that had formed were locked in. No more would be made until the first stars ignited hundreds of millions of years later. About 75% of the universe's ordinary matter, by mass, was hydrogen. About 25% was helium. Everything else, less than 0.1%. That ratio has barely changed in 13.8 billion years. The hydrogen and helium you find in the oldest stars today, in the most distant gas clouds, matches almost exactly what was produced in those first 3 minutes. The universe made its elements fast, locked them in, and moved on. For the next several 100,000 years, the universe was dominated by radiation. Photons outnumbered matter particles by billions to 1. The universe was bright, glowing, opaque. Light couldn't travel more than a short distance before slamming into a free electron and scattering. There were nuclei floating around, hydrogen and helium nuclei, but no atoms. Electrons couldn't bind to nuclei because the ambient radiation kept knocking them loose. Picture trying to build a house while someone keeps throwing baseballs at it. That's what electrons were dealing with. They'd get close to a nucleus, start to settle in, and a high-energy photon would blast them free. The universe at this stage was a fog, a glowing, impenetrable fog filling all of space. Then, 380,000 years after the Big Bang, the temperature dropped below 3,000 Kelvin. That's cooler than the surface of the coolest stars. Cool enough that electrons could finally bind to nuclei and stay bound. Hydrogen atoms formed. Helium atoms formed. For the first time in cosmic history, matter was electrically neutral, and with no more free electrons to scatter off of, photons were suddenly free to travel. The universe went from opaque to transparent in what was, cosmically speaking, an instant. This moment is called recombination, and it's the single most important event for anyone trying to measure the age of the universe. Because the light that was released at recombination, the photons that suddenly found themselves free to travel after being trapped for 380,000 years, are still out there, still traveling, still carrying information about what the universe looked like at that moment. We call that light the cosmic microwave background. It's the oldest thing we can see, the edge of the visible universe in time, and it's been traveling toward us for 13.8 billion years minus 380,000 years. Close enough to 13.8 billion that the difference barely matters. After recombination, the universe went dark. The cosmic microwave background marked the end of the universe's first light. The photons released at recombination were redshifting, cooling, fading as space expanded, and there were no stars yet, no galaxies, no sources of new light. Just a vast, dark, expanding cloud of neutral hydrogen and helium drifting outward in every direction. Astronomers call this period the Cosmic Dark Ages, and it lasted for about 200 million years. During that time, the universe was cold, dark, and almost featureless. The density fluctuations seeded by inflation were still there, tiny variations in how much matter was in one region versus another. Those slight overdensities had slightly stronger gravity. They pulled in more gas. Slowly, over tens of millions of years, clouds of hydrogen began to collapse. Smaller clouds merged into larger ones. Gravity kept pulling. And eventually, somewhere between 100 million and 250 million years after the Big Bang, the first clouds collapsed far enough, got dense enough, got hot enough in their cores that hydrogen fusion ignited. The first stars turned on. These stars were nothing like our Sun. They were massive. Some of them may have been hundreds of times the mass of the Sun, burning so hot and so bright that they only lived for a few million years. Astronomers call them population 3 stars, and we've never directly observed one. They're too distant, too faint, or maybe they've all died by now, but their fingerprints are everywhere. When they exploded as supernovae, they seeded the surrounding gas with the first heavy elements: carbon, oxygen, iron. Everything heavier than helium was made inside those stars, fused in their cores during their short, violent lives, then scattered into space when they died. From that enriched gas, the next generation of stars formed, slightly smaller, slightly cooler, containing trace amounts of metals. The cycle repeated. Stars formed, lived, died, polluted the gas, and the next generation formed from that gas. Over hundreds of millions of years, the universe filled with stars, and where stars clustered together, galaxies began to form. By about 500 million years after the Big Bang, the universe was filling with light again. The first galaxies had assembled, small ones, proto-galaxies containing millions of stars instead of the hundreds of billions you'd find in a mature galaxy like the Milky Way. But they were there, shining, and their light was doing something important. The ultraviolet radiation from young hot stars was ionizing the surrounding hydrogen, stripping electrons off atoms and turning the gas back into plasma. This process, called reionization, spread outward from the first galaxies like ripples in a pond. Slowly, over the next few 100 million years, the neutral hydrogen filling the universe was ionized. By about 1 billion years after the Big Bang, reionization was mostly complete. The universe was transparent again, but this time it stayed that way. Stars kept shining, galaxies kept forming. And the structure we see today, the cosmic web of galaxy clusters and filaments and voids, began to take shape. The first billion years of cosmic history is the part we understand least well. The James Webb Space Telescope has been finding galaxies at these early times, and some of them look more mature, more massive than the models predicted. That's a problem. Or maybe it's a clue. Either way, it tells us the early universe was busier than we thought. Stars were forming faster. Galaxies were assembling earlier. The timeline we've built isn't wrong, but it's missing details. The broad strokes are right. The first stars ignited somewhere around 100 million to 250 million years in. The first galaxies assembled over the next few 100 million years. Reionization happened between 200 million and 1 billion years. That much is solid. The details, the exact sequence of events, The rate at which things happened are still being worked out. By 1 billion years after the Big Bang, the universe looked different. It was cooler, darker in some places, brighter in others. Galaxies dotted the sky, clustered along filaments of dark matter that had been pulling ordinary matter into denser and denser regions. The largest galaxies were forming at the intersections of those filaments, fed by streams of gas flowing inward. Smaller galaxies were merging, colliding, cannibalizing each other. The Milky Way's history is written in those early collisions. Most of the stars in our galaxy's halo, the old metal-poor stars in globular clusters, came from smaller galaxies that merged with the Milky Way over the first few billion years of its existence. Our galaxy wasn't born fully formed. It was built, piece by piece, over billions of years. And it's still being built. The Milky Way is currently in the process of absorbing a few smaller galaxies, and in about 4 billion years it will collide with Andromeda and merge into a single giant elliptical galaxy. Galactic evolution doesn't stop, it just keeps going. Around 7 to 10 billion years after the Big Bang, something subtle but profound happened. The expansion of the universe stopped decelerating and started accelerating. For the first several billion years, gravity had been slowing things down. Every galaxy was pulling on every other galaxy, not enough to stop the expansion, but enough to slow it. Then dark energy, whatever it is, took over, a mysterious force inherent to space itself, pushing galaxies apart. The more space there is, the more dark energy there is, and the faster the expansion becomes. By the time the universe was about 10 billion years old, dark energy was dominating. It still is. The expansion rate has been increasing for the last several billion years, and all the evidence suggests it's going to keep increasing. Eventually, in the far future, the universe will expand so fast that galaxies beyond our local group will be receding faster than light. They'll disappear from view. The observable universe will shrink. Stars will burn out. New ones will stop forming. The cosmos will grow cold, dark and empty. But that's trillions of years away. We're still in the interesting part of cosmic history. The part where stars are shining and galaxies are colliding and planets are forming. Our Sun formed about 9 billion years after the Big Bang, 4.6 billion years ago. It condensed from a cloud of gas and dust in the outer arm of the Milky Way, a perfectly average star in a perfectly average location. Around it, a disk of leftover material coalesced into planets. Rocky ones close in, gas giants farther out. Earth formed about 4.54 billion years ago, a ball of molten rock that took hundreds of millions of years to cool enough for a solid crust to form. Water arrived, delivered by comets or released from the planet's interior, and oceans filled the low-lying basins. By about 4 billion years ago, Earth had liquid water on its surface, and by 3.8 billion years ago, maybe earlier, life had appeared. Single-celled organisms, simple, fragile, but alive, capable of metabolism, reproduction, evolution. Life on Earth has been running for more than a quarter of the universe's total history. That's a long time. Long enough for single cells to evolve into multicellular organisms, for photosynthesis to evolve and fill the atmosphere with oxygen, for complex life to explode into every niche the planet offered. Long enough for intelligence to emerge, for a species to evolve that could look back and ask where it came from, that could measure the age of the cosmos and trace its history from the first moments after the Big Bang to now. Here's what strikes me about this timeline. The universe spent most of its first few 100 million years getting ready, cooling, expanding, waiting for gravity to pull gas clouds together. Then stars ignited and things started moving fast. Galaxies assembled, reionization happened, structure formed. By 1 billion years in, the basic architecture of the universe was set. The cosmic web was in place, galaxies were shining, stars were dying and enriching the gas with heavy elements, planets were forming, and from there it was just a matter of time. Time for enough stellar generations to pass that rocky planets with the right elements and the right conditions could form. Time for chemistry to stumble its way towards self-replication. Time for life to take hold and evolve. Time for intelligence to emerge. The universe is 13.8 billion years old. Earth is 4.5 billion years old. Life has been around for maybe 3.8 billion years. Humans, anatomically modern humans, have been around for maybe 300,000 years. We're new, absurdly new. The universe ran for 13.8 billion years before anyone was around to notice. And now we're here, looking back, measuring, calculating, mapping the timeline, and finding that we can do it, that the story is knowable. Every piece of this timeline is built on observations. The cosmic microwave background gives you recombination at 380,000 years. The abundances of hydrogen and helium give you nucleosynthesis in the first 3 minutes. The oldest stars give you a lower limit of 13 billion years. The James Webb Space Telescope is imaging galaxies as they existed 500 million to 1 billion years after the Big Bang, showing you what the early universe actually looked like. The Hubble constant, whether you take the value from the cosmic microwave background or the distance ladder, tells you how fast space is expanding now and how fast it was expanding in the past. Run that backward and you get the Big Bang at 13.8 billion years ago. Every measurement cross-checks every other measurement. The timeline holds. There are gaps, sure. We don't know exactly when the first stars formed. Somewhere between 100 million and 250 million years, but the exact number is still debated. We don't know how the first supermassive black holes got so massive so fast. Some of them existed less than 1 billion years after the Big Bang and weigh billions of times the mass of the Sun. Standard models of black hole growth can't build something that heavy that quickly. Something about the early universe allowed black holes to grow faster than our models predict, and we don't know what. The lithium problem, the fact that old stars contain less lithium-7 than Big Bang nucleosynthesis predicts, is still unsolved. The Hubble tension, the gap between what the cosmic microwave background says the expansion rate should be and what the distance ladder measures it to be, hasn't gone away. These are real problems. They complicate the story, but they don't break it. The universe is 13.8 billion years old. That's solid. The sequence of events, the timeline from the Big Bang to now, is well established. The details, the exact numbers, the mechanisms behind some of the processes are still being worked out. That's normal. That's how science works. You get the broad picture right first. Then you spend decades refining it. What's remarkable is how much of this we've figured out in the last century. In 1929, Edwin Hubble published a 6-page paper showing that galaxies were receding and the universe was expanding. That was the beginning. Within a decade, the Big Bang model was taking shape. By the 1960s, the cosmic microwave background had been discovered and the model was confirmed. By the 1990s, measurements of distant supernovae revealed that the expansion was accelerating, and dark energy entered the picture. In the 2000s, satellites like WMAP and Planck mapped the cosmic microwave background with extraordinary precision, pinning down the age of the universe to within a few tens of millions of years. In the 2020s, the James Webb Space Telescope is imaging the early universe in detail, refining our understanding of when the first stars and galaxies formed. Every decade brings better data, better instruments, better models. The timeline gets sharper, and it's not done. There are still questions we can't answer with the instruments we have today. How exactly did the first stars form? What triggered inflation and what ended it? Is the Hubble tension real, or is it a measurement error we haven't caught yet? What is dark energy, and why did it start dominating the universe's expansion about 7 billion years ago? Why does the universe contain more matter than antimatter, when the Big Bang should have produced equal amounts of both? These are not small questions. They're the kind of questions that define entire careers, that drive the design of new telescopes and satellites and particle accelerators. They're the questions that keep cosmologists awake at night. But here's the thing. Even with those questions unanswered, the timeline stands. 13.8 billion years from the Big Bang to now. The first moments dominated by inflation and quark-gluon plasma. The first 3 minutes producing hydrogen and helium. The first 380,000 years ending with recombination and the release of the cosmic microwave background. The first few 100 million years seeing the ignition of the first stars. The first billion years witnessing the assembly of the first galaxies and the reionization of the universe. The next several billion years watching galaxies grow, collide, merge, and fill with generations of stars. And about 9 billion years in an unremarkable corner of an unremarkable galaxy, a star forming that would one day host a planet where life would evolve and eventually produce a species capable of looking back and measuring all of this. That's the story. That's the 13.8 billion year journey. And it's not speculation, it's not mythology, it's measurement, observation, data. The universe is telling us its history, and we've learned how to listen. The timeline is a tool. It organizes everything we know about the cosmos into a sequence that makes sense. It gives us a framework for understanding when things happened and why they happened in that order, and it's still being refined. Future telescopes, better techniques, new observations, all of that will continue to sharpen the picture, filling in details we can't see yet and answering questions we haven't figured out how to ask. That's where the story goes next. We've traced the timeline, 13.8 billion years from an unimaginably hot, dense state to a universe filled with galaxies, stars, planets, and at least one species capable of looking back and asking how long this has all been running. The cosmic microwave background gave us a snapshot of the universe at 380,000 years old. The oldest stars set a floor at 13 billion years. The distance ladder, built from Cepheids and supernovae, measured the expansion rate today and allowed us to run the clock backward. Big Bang nucleosynthesis locked in the abundances of hydrogen and helium in the first 3 minutes. And those abundances match predictions for a universe that's 13.8 billion years old. Every independent method converges on the same answer. The age of the universe is known. The number is solid. But here's the thing about science. Knowing a number doesn't mean the work is finished. It means the work is entering a new phase. The question is no longer how old is the universe. The question is, why does the universe have the age it has? What does that age tell us about the physics underlying everything? And are we sure, are we absolutely certain that 13.8 billion years is the final answer? Because there are cracks in the foundation, small ones. The Hubble tension sitting there unresolved, the gap between what the cosmic microwave background predicts and what the distance ladder measures, the James Webb Space Telescope finding galaxies in the early universe that look more mature than they should. The lithium problem, where old stars contain less lithium-7 than Big Bang nuclear synthesis says they should. These aren't catastrophic failures. They're not reasons to throw out the model, they're clues. And the next generation of instruments, the telescopes being built right now, the missions being planned for the next decade, are designed specifically to chase those clues and figure out what the universe is trying to tell us. Let's start with the telescope that's already here, because it's already changing the conversation. The James Webb Space Telescope launched on Christmas Day 2021 after decades of delays, cost overruns, and near cancellations. The final price tag was about $10 billion. The mirror is 6.5 meters across, about 2.5 times the diameter of Hubble's. It doesn't orbit Earth. It orbits the Sun, sitting at a point called Lagrange 2, about 1.5 million kilometers from Earth, where the gravitational pulls of the Earth and Sun balance in a way that keeps the telescope in a stable position. From there, it stares into the infrared, detecting wavelengths of light that are invisible to Hubble, invisible to human eyes, but perfect for seeing the most distant and oldest objects in the universe. Because as light travels across billions of years of expanding space, it gets stretched. Visible light shifts into the infrared. The farther away something is, the more its light has been redshifted, and the longer the wavelength you need to detect it. Webb was built specifically to see the first galaxies, the first stars, the universe as it existed in the first few 100 million years after the Big Bang, and it's working. Within the first year of operations, Webb found a galaxy called MUMZ-14. The redshift is 14.44. That means the light has been traveling for roughly 13.5 billion years, leaving its source when the universe was less than 300 million years old. That's shockingly early. And the galaxy isn't dim, it isn't faint, it's bright, it's massive. It contains hundreds of millions of stars, maybe more, all packed into a region a few thousand light-years across. By all rights, it shouldn't exist. Not that early, not that bright. The standard model says galaxies should have taken longer to assemble. Stars should have formed more slowly. The first generation should have been scattered and sparse, not organized into anything resembling a mature galaxy. But there it is, glowing in Webb's infrared detectors, real, undeniable, and not alone. Webb has found dozens of galaxies at similar distances, all of them brighter and more structured than the models predicted. Some of them appear to contain supermassive black holes at their centers, black holes weighing millions or billions of times the mass of the Sun. That's another problem. Supermassive black holes take time to grow. They start from stellar mass seeds, black holes formed when massive stars collapse, and they grow by accreting gas and merging with other black holes. The math says that process takes hundreds of millions of years at minimum, but Webb is finding black holes that are already huge less than 1 billion years after the Big Bang. Either the models for black hole growth are wrong, or something about the early universe allowed black holes to form faster, start bigger, grow more efficiently than anything we've accounted for. Both possibilities are uncomfortable. The early findings from Webb forced a moment of reckoning. One of the first high redshift candidates Webb detected was a galaxy called Kears 93316. Initial analysis placed it at a redshift of 16.7, which would have made it the most distant object ever observed, existing just 240 million years after the Big Bang. That number made headlines. It also made a lot of astronomers nervous because it was right at the edge of what seemed physically plausible. Follow-up spectroscopy, the method that splits light into its component wavelengths and measures the exact positions of absorption lines, revealed the truth. Sears 93,316 wasn't at redshift 16, it was at redshift 4.9. Still distant, still interesting, but nowhere near as extreme as the initial estimate suggested. The galaxy existed about 1.2 billion years after the Big Bang, not 240 million. That correction was important. It reminded everyone that photometric redshifts, the estimates made by measuring brightness in different filters, can be wrong. Spectroscopy is the gold standard. You need the spectrum to be sure. But even with corrections, even accounting for the handful of objects that turned out to be closer than initially thought, Webb's picture of the early universe is clear. Galaxies were forming earlier, growing faster, and assembling more efficiently than the standard model predicted. That's not a failure of the telescope, that's the telescope doing its job, showing us what's actually out there, rather than what we expected to find. And what's out there is a universe that was busy from the start. The cosmic dark ages, the period between recombination and the first stars, might have been shorter than anyone thought. Structure might have started forming earlier. The first stars might have ignited within 100 million years of the Big Bang, rather than 200 million. All of that changes the timeline, not by billions of years, not in ways that invalidate the age measurement, but in ways that complicate the story and force cosmologists to revisit assumptions they'd been comfortable with for decades. Webb isn't just looking at distant galaxies. It's also refining measurements of the Hubble constant using Cepheid variables in nearby galaxies. The problem Hubble's Space Telescope faced was crowding. When you point a telescope at a galaxy millions of light years away and try to resolve individual stars, the images get crowded. Stars blend together. Dust obscures the view. It's hard to be sure you're measuring a single Cepheid rather than 2 or 3 stars sitting close together. Webb's larger mirror and sharper infrared vision cut through that crowding. The images are cleaner. The Cepheids are easier to isolate. Adam Rees and his team have been using Webb to observe Cepheids in galaxies where Hubble's measurements were uncertain, and the results have confirmed Hubble's numbers almost exactly. The distances are solid. The Hubble constant measured using the distance ladder is 73 kilometers per second per megaparsec. The cosmic microwave background says 67. The gap hasn't closed. If anything, Webb has made it harder to dismiss. So what's next? Webb is working. It's producing data. It's going to keep observing for at least another decade, maybe longer if the instruments hold up and the fuel for orbital adjustments doesn't run out. But it's not the only mission on the table. The European Space Agency launched Euclid in July 2023. Euclid's job is to map the large-scale structure of the universe, measuring the positions and shapes of billions of galaxies across more than a third of the sky. The goal is to trace how structure has evolved over the last 10 billion years, how dark matter has shaped the distribution of galaxies, and how dark energy has been driving the accelerated expansion. Euclid isn't designed to find the most distant galaxies or measure the Hubble constant directly. It's designed to constrain the properties of dark energy by mapping how galaxies cluster and how their light gets distorted by gravitational lensing as it passes through the cosmic web. If dark energy behaves the way the standard model assumes, Euclid's maps should match predictions. If dark energy is doing something unexpected, if it's changing over time or varying from place to place, Euclid will see it. NASA's Nancy Grace Roman Space Telescope is scheduled to launch in the mid-2020s. Roman has a mirror the same size as Hubble's, 2.4 meters, but its field of view is 100 times larger. That means it can survey huge areas of the sky quickly, imaging millions of galaxies in a fraction of the time it would take Hubble or Webb. Roman's primary mission is similar to Euclid's: map the universe. Measure distances to galaxies using Type I, a supernovae. Study the distribution of dark matter using gravitational lensing. Constrain the properties of dark energy. But Roman has another trick. It's going to use a technique called baryon acoustic oscillations to measure the expansion history of the universe with extraordinary precision. Baryon acoustic oscillations are ripples in the distribution of galaxies, echoes of sound waves that traveled through the early universe before recombination. Those ripples got frozen into the structure of the cosmos when the universe became transparent, and they're still visible today as a characteristic scale in how galaxies are clustered. By measuring that scale at different distances, at different points in cosmic history, you can trace how fast the universe was expanding at each epoch. It's an independent check on the Hubble constant and on the models of dark energy. If Roman's measurements match what the cosmic microwave background predicts, the tension eases. If they don't, the crisis deepens. Ground-based telescopes are evolving too. The Vera the 100th Rubin Observatory in Chile is expected to start operations in the mid-2020s. It's not a space telescope, it's sitting on a mountaintop, but it has an 8.4-meter mirror and the largest digital camera ever built for astronomy, capable of imaging the entire visible sky every few nights. Rubin's survey will detect millions of supernovae, tens of millions of galaxies, and map how the universe's structure has changed over billions of years. It's going to generate so much data that analyzing it will require machine learning algorithms and distributed computing networks. The goal is the same as Euclid and Roman: constrain dark energy, measure the expansion rate, test the standard model. But Rubin will do it from the ground, at visible wavelengths, covering areas of the sky that space telescopes can't reach as efficiently. Then there are the next-generation gravitational wave detectors. LIGO and Virgo have been detecting mergers of black holes and neutron stars since 2015. When two neutron stars collide, they emit gravitational waves and light. The gravitational wave signal tells you how far away the event was. The light tells you the redshift. Combine the two, and you get a direct measurement of the Hubble constant that doesn't rely on Cepheids or supernovae or any step in the distance ladder. It's independent, clean. The first measurement, from an event detected in 2017, gave a Hubble constant around 70 kilometers per second per megaparsec, with large uncertainties. Future detections, as the instruments get more sensitive and the event rate increases, will tighten those uncertainties. If the gravitational wave measurements converge on 73, that strengthens the case that the local measurements are right. If they converge on 67, it suggests the distance ladder has a systematic error somewhere. If they land in the middle, it complicates everything. All of this, the telescopes, the surveys, the gravitational wave detectors, is aimed at answering a handful of questions that sit at the core of modern cosmology. What is dark energy? Is it a cosmological constant, a property of space itself that never changes? Or is it something dynamic, something that evolves over time, something that could behave differently in the future than it does now? If it's dynamic, the age of the universe changes depending on how you model it. If it's a constant, the age is locked in at 13.8 billion years. Right now, all the evidence points to a constant. Dark energy behaves like Einstein's cosmological constant, the term he added to his equations to keep the universe static and later called his biggest blunder. Turns out the term wasn't wrong. The universe just wasn't static. Space itself has energy. That energy pushes galaxies apart. And as the universe expands, more space is created, which means more dark energy, which means faster expansion. The feedback loop is accelerating. But we don't know why. We don't know what dark energy is made of, or why it has the density it has. If the density were slightly higher, galaxies would never have formed. If it were slightly lower, the universe would have recollapsed billions of years ago. The fact that it's just right, that the universe has spent most of its history balanced between collapsing and flying apart, is one of the great unexplained coincidences in physics. Dark matter is another question. We know it exists because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter they contain. Galaxy clusters hold together when the visible matter isn't massive enough to keep them bound. Gravitational lensing, where light bends around massive objects, shows that there's far more mass in the universe than we can see. Dark matter makes up about 85% of the universe's total matter. We don't know what it's made of. We've been searching for dark matter particles for decades, using detectors buried deep underground, shielded from cosmic rays and background radiation, waiting for a dark matter particle to collide with an atomic nucleus and produce a detectable signal. So far, nothing. Every search has come up empty. Either dark matter interacts with ordinary matter so weakly that we haven't built a sensitive enough detector, or it's something we haven't thought of yet. Modified gravity theories, where the laws of gravity behave differently on large scales, can explain some of the observations without requiring dark matter, but they struggle to explain everything. The cosmic microwave background, the formation of structure, the distribution of galaxies, all of that fits beautifully if you assume dark matter exists. Take it away and the models break. Here's where it gets uncomfortable. Dark matter and dark energy together make up about 95% of the universe's total energy density. Ordinary matter, the stuff we're made of, the stuff stars and planets and galaxies are made of, is less than 5%. We live in a universe where we don't understand what most of it is. We can measure its effects. We can build models that describe how it behaves, but we don't know what it is. That's not a small gap in our knowledge, that's a canyon. And until we figure out what dark matter and dark energy actually are, every measurement we make, every model we build, rests on assumptions that could turn out to be wrong. The Hubble tension might be pointing at exactly that, a hint that our assumptions about dark energy are incomplete. Some theorists have proposed early dark energy, a burst of extra expansion in the first few 100,000 years after the Big Bang that would shift the conditions in the early universe just enough to bring the cosmic microwave background prediction closer to the local measurements. Others have suggested that dark energy isn't constant, that its density has changed over time in ways the standard model doesn't account for. Both ideas require adding new physics. Both ideas are speculative, but they're on the table because the tension refuses to go away. There's another possibility that's even more unsettling. Maybe the universe is older than 13.8 billion years. A paper published in 2023 by a physicist named Rajendra Gupta proposed a model that combined tired light theory, an old discredited idea where photons lose energy as they travel through space, with evolving physical constants. Run the numbers and you get a universe that's about 26.7 billion years old, almost twice the accepted value. The vast majority of cosmologists don't take it seriously. Tired light doesn't work. It can't explain the cosmic microwave background. It can't explain the abundances of light elements. The standard model is too well tested, too successful at predicting observations to be that far off. But the fact that someone could publish a paper proposing an age that's different and have it survive peer review tells you the field is still willing to consider alternatives. The age of the universe is solid, it's not unshakable. Then there's the multiverse. The idea that our universe, the observable universe, the region we can see and measure, is just one bubble in an infinite foam of universes, each with its own properties, its own physical constants, its own history. Inflation, the brief period of exponential expansion in the first fraction of a second after the Big Bang, might not have ended everywhere at once. In some regions, inflation stopped and universes like ours formed. In other regions, inflation kept going, spawning more bubbles, more universes, an endless cascade. If that's true, asking how old the universe is becomes more complicated. Our bubble is 13.8 billion years old. But the multiverse itself, the larger structure, might be infinitely old. Or it might have had a beginning that predates our universe by an unimaginable span. There's no observational evidence for the multiverse, no way to test it, no way to see beyond the edge of our bubble. It's philosophy dressed up as physics. But it's a consequence of some versions of inflation theory, and inflation is one of the best supported ideas in cosmology. So the multiverse lingers at the edges of the conversation, uncomfortable, untestable, and impossible to ignore completely. Here's what all of this means. We know the universe is 13.8 billion years old. That number is robust. It's been measured, tested, cross-checked, and confirmed by multiple independent methods. The cosmic microwave background, the oldest stars, the abundances of light elements, the expansion rate, all of it points to the same timeline. But the story underneath that number is more complicated than it looked a decade ago. The early universe was more active than the models predicted. The Hubble tension suggests something about the expansion history is incomplete. Dark energy and dark matter dominate the cosmos, and we don't know what they are. The next generation of telescopes, Euclid, Roman, Rubin, future gravitational wave detectors, all of them are being built to chase those complications and figure out what's missing. The age of the universe is not a number that gets rewritten every few years. It's not like the Hubble constant in the 1970s, when estimates ranged from 50 to 100 and nobody could agree. We're past that stage. The uncertainties are small, the measurement is precise, but precision doesn't mean the work is done. It means the work is entering a phase where small discrepancies matter, where tensions that used to be dismissed as noise are now recognized as clues pointing toward new physics. The universe is 13.8 billion years old. That's the answer. But the question underneath, why that age? What does it tell us about the forces shaping the cosmos? How does it fit with what we're seeing in the early universe? Is still wide open. 20,000 people from the United States, Europe, and Canada worked on building the James Webb Space Telescope. Decades of engineering, testing, delays, and near cancellations. The fact that it launched successfully, deployed its mirror and sunshield without error, and is now sending back images of the early universe that are forcing cosmologists to rethink their models, is one of the great achievements in the history of science. Webb is working, it's delivering, and it's going to keep delivering for years. But it's not the final answer, it's a tool. A better tool than anything we've had before. And the data it's producing, the galaxies it's finding, the measurements it's refining, are raising new questions faster than they're answering old ones. That's not a failure. That's how discovery works. You build a better instrument. You point it at the sky, and the universe surprises you. The age of the universe is 13.8 billion years. The timeline from the Big Bang to now is mapped. The sequence of events, inflation, nucleosynthesis, recombination, the first stars, the first galaxies, the formation of structure, the ignition of our sun, the appearance of life on Earth, all of it is known. But the details, the mechanisms driving the processes, the physics underlying the expansion, The nature of the forces shaping cosmic evolution are still being worked out. And that work, that endless process of refining measurements, testing models, building better instruments, asking harder questions, is what keeps cosmology alive. The universe had a beginning. We know when it was. We know what happened afterward. And we're not done learning. We started with a number, 13.8 billion years. Simple, clean, the kind of fact you can memorize and repeat without thinking much about what it actually means. But now, after walking through how that number was measured, where it came from, what it tells us, it's not simple anymore. It's staggering. The universe is 13.8 billion years old, and for most of that time, there was no one around to ask. Stars burned, galaxies collided, space expanded, and none of it meant anything because meaning requires a mind, and minds took a very long time to show up. The cosmos ran for more than 13 billion years in silence. Then, on one small planet orbiting an unremarkable star in the outer arm of an average galaxy, chemistry became biology, biology became complexity, complexity became consciousness, and consciousness eventually started looking backward, trying to figure out where it came from and how long this has all been running. That we can answer that question at all is absurd. That we can point instruments at the faint glow of radiation filling the sky and extract from it the age of everything. That we can measure the distances to exploding stars billions of light years away and use those distances to calculate when space itself began expanding. That we can look at the oldest stars in our galaxy and confirm they match the timeline predicted by completely independent methods is one of the most extraordinary things our species has ever done. We are a recent arrival in a very old story, and somehow, against all odds, we've learnt to read the earlier chapters. The universe is 13.8 billion years old. You know that now, not because someone told you, but because you've seen how the measurement was made. You've walked through the evidence, the cosmic microwave background, the distance ladder, the oldest stars, the primordial elements. Every method pointing the same direction. The number is real, the timeline is solid, and the fact that we know it, that a species barely 300,000 years old, living on a planet 4.5 billion years old, in a universe 13.8 billion years old, has figured out how to measure all of this, says something profound about what intelligence can do when it refuses to stop asking questions.